Assalamu alaikum warahmatullahi ta'ala wabarakatuh, ladies and gentlemen. Welcome back to another live stream. Please join my Discord server. You can find the link in the description so you can vote on the next streams, and also you can get notified of new streams. And yeah, and also you can probably join VC if you want on the live. So instead of chatting by text, you could chat by voice if you want to. So anyways, let me try to share the link now of the stream. Copy video URL. Let's go. I still haven't took my coffee, so hey everyone, okay, live. Also join VC. Let's see. Okay, great. So I guess we could start already. So last stream we have left it in this basically. Just have these all these windows with all these triangles basically. We could basically spawn how much triangles we want, how much windows we want, etc, etc. So I've gone in more depth there, but yeah, that's a lot of Vulkan API calls. Oh my god, what's going on here? What? This wouldn't stop? Oh, it's still logging, I think, the stuff from before basically. That's a lot of calls. Damn. exit. Rust rover, okay. Alright, let me make sure my stream is good. The mic seems on, nice. Video capture, great. Okay, lovely. So let's see. Okay. Let me configure the chat. Pop out the chat. There you go. And I'm gonna put this like this. And as always, I'm just gonna have Vulkano examples as a reference on my side here. Let's see. Just so if I need anything, I could refer to it. Pretty cool. And yeah, that's pretty much it right there. I think we're ready to get started now, which is nice. All right, lovely. Let's go. So, what I want to do in this stream. So I'd like to actually add MSAA, because if you remember when we have launched render doc, right? And let's launch our application. It's annoying that it doesn't save the last executable path. So every time I have to do it, but copy path or what? Copy location, and let's go to render doc, executable path, and the working directory is the root of the project, and let's launch. Yeah, I still have a lot of that stuff. Anyways, let's just PRT screen, and we have captured a frame now. So let's see what we got. Oh my god, look at that. That's every window. What's up, DJik? Welcome to the live stream. Welcome back. How's it going? So you can see that every window we have it right here on what's rendering. And they're rendering in, oh, interestingly enough, I think they're not rendering in parallel. I think they're rendering one after the other, right? That's interesting. Can't we render all of them at once, actually? I think we can. Well, that's actually gonna be pretty interesting. Yeah, I think we could probably render all of the windows in parallel. But I'm not sure which issues would pop up that we have to fix in that case. So I guess for now I'm just gonna leave it as it is. Anyways, so what I wanted to tell you is that if you notice here, the geometry, it is very jagged. You can actually see the pixels and it looks very rough on the eyes. It doesn't look smooth. So I think I'm gonna start by trying to make MSAA so we can smooth this out. And yeah, that's gonna be the first thing. And the other thing would probably, if we have enough time, we'd look into maybe making 3D works, so like the matrices and stuff. And if we still have enough time, we could go with Lloydin meshes from OBJ format. I don't think, I'd like to later on go with glTF, but I don't think we can. It's probably gonna need its own dedicated live stream. But yeah, but it's honestly gonna be very interesting if we can sort out how to render all the windows in parallel. That would be nice. I think it should be possible, but yeah, let me see, hold on. If it's easily possible, then yeah, why not? But otherwise, I wouldn't really try for now. Let's see, where we're actually requesting redraw, we're requesting it here. Okay, where is the render function? Where we're calling the render function? I think we're calling it probably here, maybe. Yeah, here. We got self.vulkan renders, window id.borrowMute.render. And I think it's probably synchronous. Because right here I'm just requesting redraw for each one, and I think maybe it's blocks on that until it actually redraws. That's weird. I don't think that's the case, honestly. But anyway, let's just ignore this for now. Now later on I may try to find some way to actually render all of the windows in parallel, but we'll see. Anyways, so where to start? Okay, let me first of all grab some example reference here. Though I think Vulkan only have an example for like render pass MSAA, but we're using dynamic rendering, which is a bit different to set up MSAA for. Yeah, it seems like only render pass, but I'll show you how I can go, how can I do it with dynamic rendering too, because I have actually tried it before using Ash. Yeah, it's like I had a long time to figure that out because I just couldn't find anyone doing it before me. So, well, there's probably a lot of people done it before, but I couldn't find it really. But anyways, so I think the first thing first is to actually create an image, separate image of the Swapchain, which we could render to, and then we kind of resolve it. So like the image would have multiple samples, let's say 4, 8, depending on how much multi-sampling we want. Of course, multi-sampling is kind of performance heavy. So it's just kind of like basically a balance between do you want maximum performance or do you want smoothness. Usually that's basically a setting in a game or whatever. But anyways, let's see where they're creating the image. Come on, bro, there is a lot of images right here. Okay, there you go. They're creating an intermediate multi-sampled image. Let's go. And also pass the number of samples pixel choose for here. Okay, great, lovely. So I found what we need now. Let's go. Let's try to do this. So Vulkan renderer, huh? Okay, so we have our Swapchain images, but we also need an intermediary image. Do we actually need an image per? No, I don't think. But later on, maybe we can try to make like in-flight frames work or something. But anyways, for now, we only need one intermediary. So let's go ahead and say, let's see, intermediary. Should I call it intermediate or intermediate? What's the difference? Yeah, good question. What is the difference between intermediary versus intermediate? Are two different words with different meanings. Intermediate refers to something that is in between two things or at the middle point, while intermediary refers to a person or thing that acts as a mediator or go-between. I mean, that would basically be both, kind of, between two things or at the middle point. I would guess intermediary, honestly, because they're kind of like mediator between them. But anyways, let's go with intermediary image. Just English stuff. Anyways, so arc image. I probably also need an image view, isn't it? I think so. Let's see. Intermediary, and then that will receive the anti-alias triangle. Oh yeah, here there isn't just like I think an offline image, but here we have our Swapchain image, which we're gonna actually render to. And let's see where it's using intermediary. Intermediary, let's see. Do I need an image view for that? I think I do, but well, anyway, we'll see how it goes. So right now I only see an image here. I don't think, but anyways, so let's create an intermediary image now for the multi-sampling. Where are we gonna do this? Yeah, let's do it here. So let's intermediary image, and let's see how they're doing it. Image view, new defaults, image new, memory allocator. Well, can't we just clone maybe the Swapchain image or something like that, so we could inherit all of its properties, kind of? Yeah, I mean, it should be the case. The only thing that would be different from the Swapchain images would be the image usage transient attachment, which I'm going to explain in a second. And also, there is samples. There is sample 4, basically different samples. So let me see if Vulkano has some function for that to allow us to like kind of just clone the image properties, kind of. So let's say, let's get the first image, maybe, and then let's see if I clone, what's gonna happen. No, this is just gonna clone the arc itself. No, I don't want that. Makes a clone of the arc pointer. Use a borrowed data to replace, usually by code. No, probably not what I want here. Okay, what else is there here? Yeah, I don't think there is. I don't think, right? But we could do something interesting that we have learned before with Vulkano, which is basically saying image view new. I'm not sure if we need new default here. Oh, what I'm doing, image, we need actual, oh, intermediary is actually an image view. Oh, I see. Oh, right. So we're not creating an image? What? How? Interesting. But which image then? Hold on a second, I'm confused here. Let view image. Well, let me just copy this, okay? Let me just copy this, and then we can try to figure it out maybe. So here they're creating an intermediate multi-sampled image. It's explained in the introduction. We pass the same extension format as for the final image, but also pass the number of samples per pixels, which is 4 here. Okay, let me just import everything here. And let's see. Memory allocator. I think we do have memory allocator. I think it's inside of the device, I believe. Yeah, I think so. Memory. Maybe Vulkan device. Don't memory out. There you go. Okay. There you go. Okay. So here we need the format, which we should import from Vulkano. And let's go. Of course, we don't have UNorm. In our case, we have sRGB. What else? Dim2D, of course. Extend. This would be the Swapchain image extend. The Swapchain dot extend, right? Yeah, the image extend like this, I think. Let's see, but found U32.2. Interesting. Expected. Alright. Well, here's the deal. I don't think I need to specify these things, nor this thing. Though I need this one, and I need this one. Now, maybe I could do this actually. Maybe I could say Swapchain image views and get one of them basically. And like the first one, and then possibly get the info from it, like the create info from it. No? What? That's interesting. I think Vulkano does store the create info, but it doesn't seem like here. Weird. Okay, let's just go with the normal way. Okay, fine. Let's go with default here. So it's fine. And what else? So by default it's dim2D, which is what we want, and by default is indefined, which is not what we want. The extent is 0, which we should override, and the samples optimal is good. You really want to always go with an optimal tiling, pretty much. Like not a lot of times you want a linear tiling. Basically, what is the difference there is linear tiling is just like what would you expect when you load an image? You're just kind of like a buffer, like of like an array of data of color, like pixels, like RGBA, RGBA, RGBA. Like you can access it with just an index and stuff like that. Basically, just very simple data in an array, kind of, that represents the image. But in optimal, it's in another kind of tiling where basically it's optimized to access, like when you access some pixel, it's much more optimized to access the neighboring pixels. And of course this layout or this kind of image tiling, optimal image tiling, depends on the driver. Like each driver have their own optimal kind of tiling basically. It's basically to increase cache locality, because you know when you are, let's say, in one pixel, you probably never want to access like the pixel in the other corner of the image. Usually, for example, in blur, pass, for example, you would just access the neighboring pixels, which is with optimal tiling is pretty performant, usually. But anyways, so here we got the image usage, which we're gonna change, the sharing fine, initial layout. Okay. Default value is indefined. Alright, anyways, let's see. So we need the usage, we need the format of the image, which is going to be the Swapchain. Let's see, Swapchain image format, right? And the extent would be, well, actually, maybe not the Swapchain image format, but it's kind of like gotta be like Swapchain image views. Maybe we could make sure that's the case. But anyways, fine. So Swapchain image views, I'm gonna go with 0 here, and let's try to get the extent format. What is happening here? Interesting. Yeah, the image view getters doesn't seem to be complete. Interesting. Yeah, for some reason. Anyways, or maybe I'm missing something. But here, the image extent, it gives me U32.2, not... what if I set into? Would it work? Yeah, it works great. Color attachment and transient attachment. Yeah, I wanted to also explain this transient attachment. It's, well, basically the Swapchain images themselves are just color attachments, but they don't have this one. Why? Too simply because we're not gonna store the data of this intermediary image after we're done with the rendering. This is just an intermediary image. Basically that we actually render to, then we resolve that intermediary image in the same pass. We resolve it to the actual Swapchain image. So basically the final, like at the end of the day, we don't really need to keep or to persist the intermediary image data after the rendering is done. Basically, that's why we make a transient attachment, and will ever be used temporarily as soon as you have a render pass. That's why it's intermediary. So I'm in the VC. Oh, all right. Let's go. Let's go. Let's see. Hold on. Let me. Yeah. All right. Let's go. So right now it's enabled. The VC is enabled.
Hello.
Hello, how is it going?
It's going okay. I'm just watching the stream and I'm a little bit confused. The most that I've made in graphics programming was a black screen.
I get you. Like when I just started Vulkan, and like graphics in general, I would have wished I had such a stream. It's pretty long, but I try to give, like, to pour all my understanding into this long streams, basically. So personally, at least, I would have wished if I had these streams when I just started, because, like, I don't know, it's like I was super clueless. So like I could have saved a lot of time, basically. So it's been around, let me see when I joined Vulkano, for example, because let's see, because I actually tried Vulkano when I was a beginner, but I was still clueless. Because like raw Vulkan is actually kind of simpler to start with. Well, simple to actually get an understanding of what is going on, you know, like of what is the GPU is actually doing in the background. But let's see. I joined Vulkano in August 21, 2022, and I still consider myself a beginner in Vulkan. So,
well, for me, I'm a beginner to graphics, and
yeah, I'm also a beginner in graphics, pretty much.
I do DirectX stuff, but it is helpful even to look at Vulkan because a lot of the concepts are similar.
Yeah, honestly, like DirectX 12 and Vulkan, like the actual core concepts are pretty much the same. But man, I hate DirectX, like naming conventions, and like just the API in general is pretty, like I really love the Vulkan API. It's pretty clear, like the raw Vulkan API, it's pretty clear and pretty nice, pretty organized, pretty consistent. Like you can actually guess what are the names of the APIs at some point of the functions. And Vulkano is just like makes it even better, so it abstracts it on top of that of top of that raw API. And honestly, I think like starting by a normal, like a raw, simple C API for your library, and then going ahead and like creating wrappers over that raw API is very powerful, I think. At least that's what I've noticed in my experience with programming in general. Is that's pretty
Saying
nice.
you recommend the C language?
Not that I recommend the C language, but I recommend the starting with the C API. Like even I mean, most libraries nowadays does that. Like WGPU, it actually have a C API, you know, and then it abstracted through like it made some wrappers over it, or like Rust safe wrappers over it. Like let me show you. Let me show. The same thing with Vulkano and Vulkan. But basically this makes it, when you're actually starting the actual meat of the implementation, you don't care a lot about actual like abstractions and weird stuff like that and RAII and stuff. But then you just wrap it later on. But let me show you the WGPU, for example. GitHub WGPU. Let's see. WGPU. Okay, so as you can see, WGPU, for example, it does have layers. Basically, there's WGPU core dash whole or hull. I'm not sure how they call it. There's macros, WGPU types, WGPU. I think WGPU types is probably in the bottom of the stack. It basically contains all the types of WGPU possibly, I think, if I remember. And then there's like WGPU whole, which is just a very, very thin abstraction or over all the APIs that WGPU uses. Like it have a very thin API over Vulkan, over Metal, but it's unsafe pretty much. Like it's not really abstracted. It's just very, very thin raw little wrapper basically. And then you have, after that, I think you have WGPU core on top of it, which basically uses WGPU whole, but it's added, I think it added state tracking of the resources, and I think resource management too, and possibly synchronization. But though it's still not fully safe and fully Rust, like idiomatic Rust. And then you have WGPU, I think, which adds, I believe, the web and makes it safe, basically fully safe to work with, or at least kind of fully safe. Let me just see if I can find some diagram here. The big picture. There you go. That's what I'm talking about. So look at this pretty beautiful architecture. So like you have here the OS drivers, right? And then you have Ash, which they use, the raw binding they use for Vulkan, basically. In our case, we're using Vulkano, which is just a step, like just a little higher level, not higher level, but just a wrapper over Ash, but it's safe and makes it much nicer to work with Vulkan. And then we got like metal.rs. This is for Apple products. They have their own API called Metal. Then you have like DirectX 12, which is for Windows, Xbox, and Microsoft stuff. DX11, same thing, kind of, WinAPI. And there's Glow for OpenGL, basically, GLS3. And then there's WebGL here. And then all of these are just like wrapped, just a thin wrapper in WGPU-Hull. And then here you got WGPU core. And WGPU core uses WGPU whole internally with Naga, which basically they use to like in WGPU you can get like, what is it called? Yeah, shaders, you can get them in multiple languages. Like you could feed it with GLSL, you can feed it with HLSL, you could feed it with WGSL, and all sorts of stuff. And then it uses Naga to essentially go ahead and generate the shader format in what depending on which API they're using at that point. So like for example, let's say you have wrote your shader in WGSL and you have passed that to WGPU. Then what happens, it passes it to Naga, and let's say we are using Vulkan, like the API that is used is Vulkan in this current platform. Then what it does, it actually converts it into SPIV and basically feeds it into Vulkan. That's what it uses Naga for. And then you have like, on top of WGPU core, you have this WebGPU native apps, WGPU native, and then you have this GS native WebGPU apps, Deno, which I think is JavaScript, yeah. Web-based WebGPU apps, Servo, Gecko, and then you basically have the actual WGPU that like you deal with as a Rust app. For example, Bevy uses WGPU, Nano, WGPU, Valorant, Voxel Game uses WGPU, and stuff like that. In our current, in my stream, I'm using Vulkano, which means I don't have all of these restrictions. I'm just directly, just one step above Ash, basically. I'm using Vulkano. So yeah, but if I want cross-platform, like especially web, for example, I would surely go with WGPU. I wouldn't bother with Vulkan, but I don't really care about web that much. So
Well, for me as a beginner, I think it's like, for me, like I'm on Windows and DirectX. I heard that DirectX 11 is higher level. It's higher level than 12, for example, and meaning that it's more easy to understand,
yeah, it's
especially
like
more
it's
easy
kind of like
than Vulkan.
OpenGL, but a bit better, a bit more aligned with the current like
Yeah.
modern stuff. But honestly, I
I
wouldn't really recommend it. Like at some point, I was very exhausted of Vulkan and like modern APIs in general, and I just wanted to fall back to OpenGL or like the other higher level APIs. Like I was struck by the bad debugging infrastructure there. The API is super stupid, super. Like I don't know. I just didn't like. I find myself. It's kind of like in Vulkan and DirectX 12, for example. Like in modern APIs, you kind of like just pay the pain up front. Even in Rust, like with the borrow checker, you just you pay the pain up front. You pay the work up front, and then later on in your actual game loop or your for the rest of your life or for the rest of your projects, then you become relaxed. But in something like OpenGL, what happens is that you're pretty relaxed at the beginning, but then when you come to some actual advanced stuff, there you go. Now, let's say your shader is not compiling on some platform and the only error you have is invalid parameter error. Yeah, figured it out. Or invalid
Yeah, that
error.
sounds pretty bad.
Like especially the validation layers, for example, and the layers like the Vulkan layers, it's pretty cool concept. Like I wish a lot of the APIs actually use such a thing. But basically here, I can just run vkconfig from the Vulkan SDK, and then I could use whatever layer I want. Let's say validation, which tells me if I'm using the API somehow wrong. Of course, it wouldn't catch everything, but it would catch anything that is obvious. And then there's the API dump, for example, which I could, or otherwise I could just disable all layers. And this is what would be the best performance basically, and what would your user actually go with. But here, the API dump, if I do this, and I run the application, I would basically see the API calls. Right now I have this stuff going on here, but basically you see all the API calls happening in Vulkan, what they return, what the parameters are. It's pretty good debugging experience, honestly. It's pretty straightforward. That's why I like Vulkan basically, or at least one of the things why I like Vulkan. But yeah. So yeah, hopefully that clears up a bit. But API dump. For now, let's just go with validation. And yeah, I think let's go back right now to the actual stream. Yeah, as you can see, for the WGPU uses Vulkan in Windows, Linux, Android, and Mac OS, iOS. It uses Molten VK, which is an abstraction over Metal. And then it could also use Metal itself directly. Then there's DX12, DX11. They're working on it. Just for compatibility basically. Then there is OpenGL, okay. meaning down level best effort support, not first class. GL 3.3 plus, and then there's GLS, which is like OpenGL. What is it called? Basically embedded for embedded systems, and then there is, or like Android, for example. Yeah, basically. And macOS iOS requires the angle translation layer. Oh my god, that's another layer of abstraction right there. And then there's WebGL2 here, and WebGPU, which is the new API that would replace WebGL. But yeah, I honestly prefer Vulkan if I really don't care about cross-platform. Otherwise, I would go with WGPU.
For me, today I woke up and the first thing that I did was try to make something in DirectX. And I think it took maybe up until 5 p.m. to kind of learn all of the setup process. So the first thing that I did was use Win32 API to initialize a window, create a window instance and a window class and all that, and then set up the DirectX device in Swapchain. In DX11, there's a function called create uh, create device and Swapchain.
Yeah.
And in there it kind of like you input a bunch of arguments and it kind of automatically like figures out some stuff for you. Like in Vulkan, if you were to make the device and swap chain, would I have like how hard is that? Because in DX11 it's pretty easy.
I know what you mean.
Is
I
it?
know what you mean. That's what I wanted. Why I wanted at some point to use DirectX, because like Vulkan is trying to be super inclusive of all hardware possible. So you end up with a bit of a tricky situation where you like have to like to make the API very verbose and like and more flexible just to support as much platforms as possible. While in something like DirectX, you don't have that. Like it just supports the Microsoft system, so you don't have to do some extra steps to actually do that, basically. But I know what you're talking about. Like for example, here, if I want to create a swap chain, I'd have to make sure to enable some extensions, like in the Vulkan device. Sorry, not here. Where did I do it? Hold on. Vulkan instance, right? So in Vulkan instance, like I have to make sure to get the required extensions of the surface, which would go ahead and figure out, am I in the Android platform or am I in AppKit, UIKit, Windows, Wayland, XCB, XLib, whatever. And then it would like go ahead and enable the extension that is needed for that. And then I would have to figure out, like, am I on Mac OS? Then I would need to enumerate portability, because on Mac OS the Molten VK, which is just like over Metal, because there's no native support for Vulkan in Mac OS or Apple products in general. So I have to say enumerate portability, meaning I'm consenting to the fact that I have to be careful to support, let's say, Apple products. And here, KHR swap chain. I'm also like doing the extension KHR swap chain here. I'm adding it here. Why? Because, well, you could use Vulkan without a swap chain, without any of that stuff. Like you could just render to an image, or like just have a headless server, or just doing compute basically, or something like that. So it's very, very flexible, and that's why you end up with all these kind of verbose API and all sorts of weird stuff, basically. That's why DirectX is kind of easier to set up when it comes to cross-platform things, like relating, for example, to the swap chain, let's say. But the other thing that I didn't like about DirectX, it's pretty hard to find some actual good resources. Like for Vulkan, I wouldn't say there's perfect tutorials, but there is a lot of resources still. The API is pretty intuitive once you get the hang of it, kind of. But yeah, so yeah, that's pretty much what I have to say about that.
All right. Well, my ultimate goal is to make game engines for like develop proprietary game engines for companies and like work at like maybe a game developer making engines. So that's why I was getting into DX. Vulkan does, everyone talks about how hard it is, and so that kind of scares me. But maybe I'll try it, see how much I can make in a week or something.
There is some things pretty hard about Vulkan, like for example synchronization. But in this case, for example, Volcano handles that for you. Though it's kind of Volcano synchronization currently is not the best it can be. But in future version, they would actually, instead of using futures, they would use a task graph. At least that's what the maintainers told me. So that would be like another step forward for Volcano. So you pretty much don't have to deal with such complicated requirements of alignments and weird stuff like that. That's all done for you by Volcano. And hold on a second. Okay, alright, back. So basically what I was saying is that when dealing with raw Vulkan, you have to do the synchronization yourself, and you have to care about like requirements. For example, the requirements of memory, of buffers, which memory is best, and creating your own allocator of memory, etc. Which is very tedious, hard, and you have to like read the whole spec to make sure you're not doing something funny. But Volcano in this case is doing all that hard work for me, and honestly, Rust is pretty much like I have experienced a lot of APIs before, a lot of languages. I actually have created a triangle, Vulkan triangle, in a lot of languages like Rust, Zig, C, C++. What else?
Go.
No, not really Go. I never really gone too deep with Go actually. Yeah, it's pretty much I think C, C++, Zig, Rust, and also in C++, for example, I also used Vulkan HPP. So yeah, I pretty much used a lot of abstractions in a lot of languages. And actually, it's a very good test to check out on the language to see how, like in terms of system programming, of course. You wouldn't have like you wouldn't go with JavaScript or Python to write a Vulkan program, though you could do that, but I wouldn't recommend it. So yeah.
Yeah, for me, if I want to get hired, I should learn C++, probably for games. So if I do Vulkan,
But I think
I
that the ecosystem is slowly transitioning to Rust, kind of, to some degree.
really
Like
now.
especially Microsoft right now, it seems to be pushing hard on Rust. And how much Rust how much employees in Windows or like sorry in Microsoft. Let's see, Microsoft employees. Look at that. Microsoft had what is this? 221,000 full-time employees worldwide. I think it's the whole city right there, or actually more than that. I don't know. It's a
Yeah.
lot, bro. So yeah, Microsoft is actually pushing towards Rust nowadays. It's like pretty much like 70% of problems in Microsoft is related to memory problems, memory safety problems, which Rust is trying to fix with the borrow checker, basically. But yeah, but honestly, Rust APIs like idiomatic, safe Rust APIs are very, very good at their job. It's pretty good.
I will look into it and try to make some
I
projects.
I also bet on Zig, but I would use Zig for lower level stuff where like I'm more into the hardware, I guess, and I'd like more control over the types and comp time, basically. But like for example, when Zig becomes like released fully, I think I may start to use like Zig and Rust at the same time. So like Zig, I would write in safe code in it, and then I would like in a C API kind of thing, and then I would wrap it in Rust with like a safe wrapper, basically a RAII wrapper or something like that. It's just kind of like WGPU, but WGPU is actually doing everything in Rust. But I would probably at some point when Zig releases, I would try to just write, like for example, my Vulkan in safe code, I can write it in Zig, and then just call those in safe functions from, like wrap them actually first in a Rust kind of idiomatic wrapper and safe one, and just use that in my program. So basically I would use both, like I don't have to choose. I can use both Zig and Rust, but currently Zig does have a lot to actually become a good programming language. There's still a lot of work on it, so, and it's still not released yet. So
Also, what is SPIV?
SPIV is kind of like assembly.
Oh, I don't need that.
But basically what's happening is that in OpenGL, the problem they had is like you would write your shader, but then you wouldn't compile it. Who would compile it is the driver. So each driver was actually writing their own GLSL compiler. And the problem you had with that is that some compilers actually followed the spec up like to the dot, but some other compilers or some other drivers was kind of relaxed on the spec. So what would happen is that in one system or in one driver, your shader would compile just fine, and then another driver your shader wouldn't compile because your shader isn't fully spec conformant, because your own driver that you tested the shader with was kind of relaxed on some requirements or kind of relaxed on some spec stuff. So how they fixed it in, let's say, Vulkan, they have introduced SPIV, which is much lower level than, let's say, GLSL. GLSL is kind of higher level. But basically you could use GLSL, you could write your code in, or your shader in GLSL, HLSL, or whatever language. As long as you can actually compile it down to SPIV, which is a bit like assembly or bytecode, kind of like JVM or the Java bytecode. And then basically you would actually give the SPIV to the driver, and then the driver, instead of having a full-blown GLSL compiler, it just takes that SPIV and it kind of translates it or map it to their own proprietary assembly for the GPU basically, and then just simply execute it in the GPU. Like, yeah, basically. Hopefully that makes sense.
Yeah.
So it's basically like this, where instead of the driver doing everything in Vulkan and like DirectX 12, a lot of things you do it yourself in the app, or you rely on some library, which is fine. But like having multiple implementation in every driver, that's where you end up with a lot of that headaches. In fact, that's where like you have indefined behavior in C and C++. So what happens there is that instead of just like Rust or some other languages where like you have one implementation of, let's say, Rust compiler basically, but in C and C++, like there's multiple implementations of the compiler. Like there's just a spec, and there's also indefined behavior. Now, indefined behavior is actually intentional, wise as to allow the freedom for the implementations to optimize depending on their indefined behavior. So like even for example in Rust implementation, there is some indefined behavior, and that becomes when you write in safe code. The thing is, now the Rust compiler actually uses the guarantees that the borrow checker guarantee for you to actually optimize even further than it could like in a relaxed language like, let's say, C or C++ basically. But yeah, it's basically for optimization, but then you end up in all these implementations, which some works, like your program would just work fine, some other it would crash. So yeah, basically that's what's happening right there. Right now in Vulkan, you actually either write you write the shader compiler yourself, you write the allocators yourself, and you have full control over everything. Like the driver is very thin. The Vulkan driver is very thin. It just like translates or maps almost directly to the underlying hardware. But yeah, pretty much.
So you're saying that I can learn HLSL right in that, and something can translate that to SPIV for me?
Yep, exactly. And then you could use it in Vulkan. Or you could write in WGSL and then use, let's say, Naga and just translate that to SPIV and use it in Vulkan. Or you could write your own shaders in SPIV directly. Or like you could compose them in your program at runtime. Like you could compose the instructions and then execute it at runtime. Or let's say what you could also do, for example, is create your own compiler, your own SPIV compiler. SPIV is not that complicated. I mean, it's kind of complicated, but not that complicated like, let's say, LLVM or... But you see what I mean, basically? You could write your own language, your own shader language. As long as you can translate it to valid SPIV code that is compatible with Vulkan, you're good to go. What I like about HLSL is that it's kind of like... GLSL is kind of like more like a C API kind of thing, you know? And HLSL is closer to, let's say, higher level languages like C++ and Rust and stuff like that. Basically, you have more type safety and some other cool stuff. But yeah, pretty much.
And where should I learn the fundamentals, the abstract, the theory of computer graphic rendering?
That's hard.
To the point where I can...
But I think
read about
Learn OpenGL does have a lot of cool articles for beginners, like for beginning, like yeah, I think OpenGL, this guy right here, this blog is pretty good. It have some pretty cool articles, and then you could try to map it to Vulkan or whatever thing. Like it's fine. You could just follow with this tutorial, for example, to start with, and just use OpenGL for now. Why not? It's fine. And just go with this and just focus on the actual, not the OpenGL specifics, but just like what is happening. Like it's pretty much like the graphics itself is very similar. It's just that it's kind of different way of doing things, basically. But the core concepts are pretty much there, really. So vertex attributes, stuff like that. And like, let's say, for example, you want to learn about, let's see, for example, advanced lighting, okay? Let's say you want to learn about parallax mapping. Then you could come here, you could read about it, you could see some stuff right here. You could try to learn from it, basically.
How much math is this?
The thing is, I was super bad at math. Like, not really super bad, but basically, I wasn't a fan of math, right? But when I actually started on shaders, at first it was very hard to get into the mindset of shaders and stuff like that and how they work. But actually, shaders really helped me learn a lot of math. And because you can actually see your equations like in real time, what is happening. Like you try an equation, you see what it does. It works this way. You try to change this variable or change that, and you see what happens and what is wrong, you know. And like, you know, in school, you usually just learn abstract rules and there you go, done. No actual, like, you don't see that stuff interactively. There's also like, what is it called, Desmos, which is a pretty good website that I actually very much enjoy. And like, I could just write whatever equation or whatever and see the graph of it and try to like play with the variables in the equation itself and see what happens, what changes, and like, yeah. So like, let's say ax to the power of 2 plus bx plus c, you know, and then I could make these variables and see what changes. Like when I change a that multiplies by x to the power of 2, what changes? I see that the graph actually kind of like becomes thin and and stuff like that. So I kind of like learn math visually more. I don't really enjoy the abstract stuff, and the graphics programming and shaders are very visual. So I really learned a lot of math through shaders pretty much, and graphics in general. So yeah, and you could like play with variables and see what happens. um, like you could make points, like let's say let's just say 0c for example, and then you could see what happens. And let's say b, let's set it to 0. And then for example, let's say I want to basically, for example, go ahead and take this graph and let's say translate it left and right. So how I can do it? Well, I have this x. I could wrap it, for example, in this brackets, right? Then I could do minus something. Let's say minus d. And there you go. So now what I could do is dc, and then I could play with the graph however I want. And then wow, let's say dc, I don't know, let's say something like this. Not really, minus a, for example. Not really, but yeah, I think you got the point here. But I may actually make some video about this later on, to go in more depth about this. Also, let's say for example the actual, let's see, x to the power of 2 plus y to the power of 2 equal to r to the power of 2. And I got a circle. Equal to R2 basically means that, well, I'm getting the border of the circle. If I do less than R2, then that means like the actual inside of the circle, and doing it like this. And now the thing is, and this is actually how shaders work, using such functions like this, because, well, in shaders they're embarrassingly parallel, which means that like you gotta use some math to figure out what to do on every single pixel in parallel without having to synchronize it between each other. Now in every, like for example, the pixel shader runs for every single pixel, and it gives you the x and the y of the pixel, right? Then you could use, let's say, the x and the y to figure out if it's, let's say, greater than the radius of some circle or equal to the radius. And then you could color it with something. Like, let me show a little example with Godot, for example, here. Real quick, new project. Shaders real quick. I'm gonna try to, oops. You could use what, or actually you could also use Shader Toy, but I'm just quite comfortable with Godot, basically. Let's see. Come on. All right. Let's say I have some, I don't know, maybe some rect, color rect. Let's say, okay, let's do this. And let's say I'm gonna add the shader to this. How do I do that? Material. You can assign a material. Actually not this, let's see, new shader material, right? And new shader, whatever. Who cares? Let's go create, and yeah, we have a shader right now. Here I can write whatever I want in the fragment. Let's say color equal vec4, vec3, 0.0, 1.0 here. Let's save. So I got all the pixels are black, you know, but like if I change this, this is basically I'm putting the same value on X, like on R, G, and B. And A, I'm just setting it to 1. Let's say 1.0, 0.5, gray. So basically it's grayscale because R equal G equal B, stuff like that. Now the problem is here is that all of them are the same color, so you get this constant color basically. Now I need to figure out some way. Let's say I want to make a gradient. Now how can I change the color of the pixel when I only have X and the Y, which are basically the UV? So what I could do, I could say UV.X, basically color it depending on the X of the pixel. Like here, the pixels that are in this side have like X equal to 1 basically, and here X equal to 0, and between them, 0 here, 0.5, 1, blah, blah, and you get this gradient. Let's say I want to make it the other direction around. I could say 1.0 minus, oopsies, UV.X, and now I have inverted the gradients. Let's say I don't want the gradients to just change in the x-axis, but also dependent on the y-axis. So let's say diagonally. So I could, for example, say UV.X plus UV.Y. Basically, I need to involve the y-axis so I can change depending on the y-axis. But yeah, let's say I want to make an animation. What variable changes depending on between each frame? Time. So I could use time to do some cool stuff. I could say sine of time, for example, and then I have this animation. Now let's say I want to also offset the sine wave depending on the pixel position, the UV.X, and let's go. Now I got an animation. Though here,
genius.
The sine wave should be 0.5. But yeah, you'll think that I'm genius, but pretty much I actually learned most of this math just from shaders, pretty much, and just playing around these equations, seeing what variable changes, how to do something. And yeah, it's just like shaders and Desmos, pretty much, mostly.
How would you introduce a parabolic function into the shaders?
What do you mean by parabolic? X to squared?
Like
for example, let me show you some other cool example here. Let's say I want to draw a circle, but the thing is I only know the X and the Y of the pixels. That's all I know. Basically this function runs for every single pixel, and the only input it gives me is the X and the Y, because shader should be parallel. So how can I write, let's say, a circle? Well, I could do this. I could say if let's get the X first. Hold on. Float X is equal to UV.X. And then float Y. Or actually, also, let's just say, yeah, it's fine. Let's just say if UV.X to the power of 2 plus UV.Y to the power of 2 is less than, let's say, 0.5 or something like that. And then if that's the case, then we could say color equal to something. But what is happening here? Invalid arguments operator plus int float. Hold on. Well, this is basically the R of the pixel. Hold on a second. Let float R is equal to this. Maybe this should actually be UV.X like this. Maybe shaders doesn't support power off. Yeah. So if R is less than 0.5, then I could color it with something else. Let's say color is equal to vec4, vec3, 1.0 for the alpha, and I could say vec3, let's say 0 or something. There you go, we got a circle, but it's right here. It's centered on 0, 0 coordinates. Now, how can I actually change the center of this guy? Well, I just gotta wrap all the x's and all the y's in my equation, and let's say I want to change the x-axis or and the y-axis. Like I have this variables minus a minus b. So instead of plugging in x or y directly, I just subtract some value from it first. And there you go. Now I have a and b to change. And I could even make this, and now I could change it however I want. Let's say I want to change the radius. How to do that? Well, let's say okay, hold on, get it back. We could say a comma b, for example, plus r, and there you go. Now I could change this, I could change that, and so on. Maybe a plus r comma b 2, and there you go. Or otherwise we could even say a plus r, b plus r, and there you go. But yeah, stuff like that. And now I could plug this in. Now in here, instead of passing in the UV directly, I'm just gonna store it. Let's say vec2 UV is equal to UV. Then I could say UV here. Right? So right now I haven't changed anything. I just made an intermediary variable. And now I could go ahead, UV minus equal to vec2 A and B. And let's make these uniforms. Uniform float, let's say uniform vec2 actually A. Let's say offset or center or whatever. And actually just use that directly. And now if I go here, shader parameters, and I could play with this center. But it's too big actually, and let me make this squarish. Let's see, let's make it 648. Okay, and let's also make the uniform float radius, for example. Let's go radius. Now I could also change the radius. So here I could go ahead and say, hold on, I'm doing something wrong here. Oh yeah, I see, because I haven't changed all of them. Makes sense. And now let's make this 0, 0. And what is happening? I'm doing something wrong here. Oh yeah, radius. So now I could change the radius of the circle. I could change the center of the circle however I want. See? And yeah, let's say I want to actually create right now, let's say a sphere instead of a circle. So that means that I'm gonna also have, and just to make this simple, let me remove all this. So currently I only have x to the power of 2 plus y to the power of 2. Let's say less than or equal to or less than some r to the power of 2. And there you go, I got a circle. But let's say I want the z-axis now, I want 3D. I could just add plus z to the power of 2, but the problem is I don't have z. How can I get it? Well, the thing is, if I know r, what we could do is I could say, let's just say this, hold on a second, let's just simplify it to x to the power of 2 plus y to the power of 2 equal r2. What we could do is we could take this x to the power of 2 and put it here instead on the other side of the equation. Minus y to the power of 2, same thing, we're just gonna flip the sign. Just pretty simple arithmetic. And here like we would have plus z to the power of 2, but right now we're gonna have z to the power of 2 equal to r to the power of 2 minus that. And with that, now if I want z itself, I could remove the power from here, and then I'll have to make a sqrt here, a square root, and there you go, I got z out of r, out of x, and out of y. So here I could do it. Let's say float z, so I could say r times r minus minus x to the power of x, well, uv dot x to the times uv dot x minus uv dot y times uv dot y. Now I have z. Now let me actually use that. I'm just gonna say color equal to z. Oops. And what is happening? I'm doing something wrong again. uv dot x. Oh yeah, I see. So what's, oh yeah, I'm not taking into account the r for some reason. Oh, I see. So this should be radius. Now there you go, I got the z axis. And then you could see kind of like it is kind of a spherical kind of thing. And now what I actually need to make this real 3D, I need to add lighting. Otherwise you just see this. What I could do then, I could get it normal out of my sphere. Now I do have x, y, and z, and to get the normal of a sphere it's pretty simple, just x, y, z. And so how to do it? Well, vec3 normal is equal to vec3 x, y, z. And then normalize it. I don't remember how to normalize a vector. I mean, it's probably normalized here, not sure, but just making sure it's normalized. And node identifier and expression. Oh yeah. Or I could just say UV here. And there you go. And yeah, right now I got my normal. Now I need to calculate the actual light intensity. And basically light depends on, like, now we got the normal of the surface, right? In that specific pixel. So now how would we calculate the light? Well, we have the normal. We also need to have some sort of, let's say some light direction, right? Some light ray. Depending on when the light is going, we can figure out the intensity. So we know that cosine, when both the rays are like kind of equivalent, not equivalent, but like in the same direction, we know that you get the full intensity. But when it's like perpendicular, it's zero intensity. Well, there is some function that is similar to this properties, which is cosine. So sorry, not cosine, dot product, right? So what we could do is float diffuse is equal to dot product of the normal with, I don't know, let's see. Yeah, we need some light direction. And if we take here, let's just make sure that the light direction is also normalized. Okay. And then here, uniform light direction is equal to vec. Well, I'm gonna set it from here actually. And expected data type, right? This is gonna be vec3. And now I could use, instead of z, I'm gonna go with the diffuse that I calculated, basically the lighting. And if I change the light direction, you can see that I have some light. But hold on, I'm doing something wrong here. Yeah, hold on. Oh, the radius is... Yeah, I'm missing out on something here. Let me see, diffuse, the normal. The Z. Yeah, I'm missing something here. The norm. I mean, you could kind of see like a moon right there, but yeah, I'm doing something wrong here. Normalize vec3 uv comma z. If I use the uv instead like this. No. Let's see. Yeah, I'm missing something here. I don't know. Normalize vec3 uv. Yeah, I don't know. I'm missing something here, pretty much in my calculation. Not sure what it is. uv.x minus uv.
By the way, while you're thinking, can GD shader be converted to SPIV? Ooh.
I'm seeing basically the normal now, but I guess the normal seems to be fine, maybe. Like in the axis. Yeah. Well, the thing is, Godot uses Vulkan. So basically this is just kind of like it's basically GLSL, but pre-processed by Godot and, composed together. And then essentially being translated to SPIV and then given to the shader API, to the Vulkan API. But I'm not sure what I'm really missing here. Damn, dot normal.
Is it supposed to look like a sphere with light shining on it?
Yeah, exactly, but I'm not sure what I'm missing here. It's probably some stupid thing that I've not noticed. This is crazy. Okay, let me try to redo this though. Let me try to redo this for a second here, because I cannot really see what I'm going wrong here. Okay, so let's see. First of all, we're gonna need the UV. So let's just say, well, let's just take the z-axis directly. So float z is equal to r, which I'm just gonna hard code for now, to 0.5, let's say. And also, let's just say vec2 uv is equal to uv, so I can change it later if I want to. Now minus x times x minus y times y. So basically float x is equal to v dot x and float y is equal to v dot y. That's this axis. By the way, I haven't shared my stream with Vulkano server. Forget about that. Let's see. We could share it with server there too. Just in case someone interested there. Anyways, all right, let me try to figure out where I'm going wrong here. Vec3 normal is equal to Vec3 x, y, z. And then I'd like floats. And let's just say light direction, let's just hard code that too. I don't know, let's say for now 0.0, I don't know, minus 1.0, something like that. And then let's say float diffuse is equal to dot product between n and the light direction, or basically L. Okay. And then color Vec4, Vec3, diffuse, 1.0 here. Great. Right, but let's see. What? I'm super confused right now. Float R. Seems like my R is not even getting... What? Oh my god, now I see. I'm missing a SQRT here. Damn. I'm missing a square root here, I think. And now what I'm missing else? Square root, right? Square root is what I'm missing here. Yeah. R to the power 2 minus x to the power 2 minus y to the power 2. Okay. Now what I'm missing else? Yeah, let's make these uniforms now. Uniform R, float, I think, or uniform float R. Okay. And uniform Vec3, light direction. And let's see, so no longer we need the R here, or let's just call this L. And now let's remove this from here, but I gotta make sure that N and L are normalized. Just to be sure. Maybe normalize actually. Okay. There you go. But something is weird there though, still. Yeah, there you go, look at that. Okay, let me grab a center too, so uniform Vic 2C And then basically UV minus C minus the offset or center. And let's go. 0.5 and 0.5 here. Let's decrease the radius and let's go. Look at that. Oh my god. Isn't that a sphere?
It looks like a sphere. Is this how spheres are usually calculated in graphics?
Not really, because this is quite inefficient. Because you're doing the calculations for every single pixel. And imagine that you have all of like games nowadays and applications like have a lot of this geometry, and in fact even more complex than this. And in fact they're not even abstract shapes like a sphere, which you could just make a equation for. So you have the vertex shader too, and you have geometry and you have like triangle rasterization, and that's how it actually works basically. And in fact we could make this smoother. Like notice here that it is very jagged, so we could say this is gotta be the color basically. So uniform color. So all of this just using math, pretty much nothing crazy, on every single pixel in parallel. So
By the way, what is a uniform?
Uniform is basically so I can pass it from the CPU to the GPU to the shader basically. In this case, so where is it? Hold on, let me actually fix this first. Vic3 color, or let's just say Vic4, who cares? Yeah, no, let's go with Vic3. And here I'm gonna say actually diffuse for the alpha. Oh well. Well, that's not exactly what I want. No. Hold on. So Vic3 color times diffuse. So I could modulate it by the color. And then here in the alpha, I'm gonna go with Z actually. Yeah, I'm gonna go with smooth lerp. Z. I don't know. Let's say. Let's try this out. Smooth lerp call expected mode 0. What? Smooth step, yeah. I see. And let's go. Rich. And actually, let's say 9 and 51. Hold on a second. There you go. What is happening here? No, I'm doing something wrong. What is the color I'm setting it to? Actually, this should be color. Let's say red, for example. See?
What is causing the color to only be on the circle and not everywhere else?
I'm using the z-axis, I'm clamping it. If it's like between... And hold on a second, I want to also smooth this out. 0.4, what about that? Or maybe 5, 6. Weird. Uh-oh. Look at that. Not really what I want. Oops. No, I'm doing something wrong again. Not really. Oh, the parameters are different, I see. The value goes here. Okay, now I can play with this. Honestly, give me some uniform. Not really. Yeah, that's exactly what I want. So I want B. Great. Let's go. Okay, so 0 would be 0. A would be 0. And B would be the actual smoothing, which we're going to do in Vulkano, but we're not going to be doing it this way. Smooth in, and let's go with here B. Okay, so right now I could change the smooth in here, so I could like kind of like multi-sampling to some degree, so it doesn't look rough. And now I could, you know, yeah, this can't be done. Let's make a new scene here, and let's first of all make a 2D scene. And let's put this guy, oh, because this is only UI node, I see. Color rect, let's say, let's go, yeah. And I could easily change the lighting, but it's kind of hard to change the lighting because, you know, it's a vector. And you don't like get a normalized vector here. What would be more intuitive is to use the angles instead, like to be able to change the angle of the of the light instead of vector of normal, or like, sorry, the light direction. So what we could use for that, we could use, what is it called? There's some other coordinate system, spherical coordinate system. So all of this math I learned through shaders, pretty much. I really just learned through shaders. Spherical coordinate system. And yeah, you could give it like one angle from here and one angle from here, and an R, a radius, instead of giving it like raw vector 3 direction. So yeah, where's the, let me get the equation for that. Where is the cosine and sine here? R cos, there you go, here you go. The, what is it called? The parametric equation. This is the parametric equation where like you give it, I don't actually remember what the, I don't know how to explain it, but let's see what they say. Parametric equation. Equation is a set of equations that express a set of quantities expressed as functions of a number of independent variables. What the? Like, this is why I hate school. Like, bro, what would you learn from this? Anyways, basically, given this R and this like angles, you can get the X and Y and Z. But anyways, so essentially, so instead right now here, instead of passing, where is it? Instead of passing a direction of the light, and let me just make this a little easier to read. The radius, and what else here, the light. instead of light direction, I'm gonna go with light angles. So, and I don't really need the radius. I'm just gonna go with Vic2. Or let's say maybe light rotation, for example. Or
You said that
something like that.
with this coordinate system, you can
Use like kind of angles. So
you
instead of
can plug in the angle and the radius.
yeah, so instead of basically
And
plug in X, Y, Z, which is super intuitive for such a use case, you use another coordinate system. So as to here, you basically plug in the angles, the theta, and I'm not sure what this is called, but basically the two angles in this direction and the other direction. There's also polar coordinates, which are just in 2D. But I'm gonna explain this more later on. But basically you plug in these two angles and this radius, and then you get back the X and Y and Z, the actual vector, the direction. So the user, instead of having to like plug in a light direction, which is super intuitive, he passes angles and then he calculates the direction. You see what I mean? So let's see, hold on. So the radius and the light direction here, this is the normal. Yeah, and valid arguments for built-in .fic. What? I'm passing in Vic2. Oh, I see why. So for that, well, yeah, we're not gonna pass light rotation directly. We're gonna say, I don't know, spherical coordinates or something. Spherical chords, and then pass in the angles, the light rotation or whichever. And I'm sure it's gonna be normalized for that one. So let's just go with Vic. So this function would give you back a Vic3, and it would just take spherical chord, like it would just take rotations, so angles basically. So here I'm gonna say this gotta be Vic2, and here I'm just gonna return Vic3. So Vic3, in the X we're gonna go, I think, with the cosine of rotation. Let's see. Yeah, let's just go with the first angle basically, and then sine of rotation dot y. This is polar coordinate system. I just have cosine rotation dot x and sine of rotation dot y basically, and you only give it let's see if I change this here. Yeah, it's one directional, you know. But if we want to extend it to 3D, meaning spherical coordinates instead of just polar, we need to add times, so like times cosine of actually, hold on a second, I need the sign here. Yeah, my bad. So here we're getting, well, actually just keep it like that, really. So this is very intuitive. I'd like to put it as cosine, yeah, and sine first. So these are the polar coordinates. Then you add the sine here and the cosine for the z, basically. So this is basically the polar coordinates, and to extend it to 3D, you add sine here of rotation dot y, and here same thing, sine, I believe, right? Sine. I don't need the r because it's basically 1. It's going to be normalized. Rotation dot y, and here finally I'm going to say cosine of rotation dot y, right? And now I could actually change the light rotation. Yeah, I'm doing something wrong here, maybe. No, I think hold on, what? Yeah, I may be doing something wrong here. Let me make sure I'm doing this right. Spherical coordinates, we're passing the light rotation. And then here we got Sine, sine, cosine. Sine, sine, cosine, and cosine, sine. That should be correct, or maybe I'm missing something here. Oh, I see. So here this should be sine of rotation of x. I don't know how I missed that. And there you go. Right now I could actually use the rotation instead. You see? This is very cool. Now you notice that there is no like lighting at all in the direction in the other direction, because basically the cosine, like the dot product, gives you 0 when the light is actually in like, what is it called, what is the other term? I don't remember, but basically it should be like this. Right? When that's the case, it becomes 0, and if you go in the other direction, it just becomes -1 pretty much. So I actually, to make sure that this is correct, really, I should make sure to that this doesn't go below 0. Pretty much. And then I could add some here, some what is it called? Some ambient lighting. Like in real world, in real world, what you have is like, you have reflections of the light. That's why you never really see an object totally black in the other direction, because it's just the light bouncing to other places, like in the wall or whichever, and then it's bouncing back to the other direction. So you can see some light, but a lot of times in graphics, a lot of things are pretty much just simplified, because we simply don't have the compute power to do all of that. And that's basically what ray tracing is. Like, it basically bounces light. It actually simulates how real light actually works. But this is just like calculations and just kind of trying to simulate it to some degree, at least to the point where the human eye could kind of see something there. Anyways, so for that, what we could do, we could add some ambient lighting. Let's say ambient light. And then we could add that, let's just offset it here, I think. Vec3 diffuse times color plus ambient light. And actually, ambient light, let's just, instead of color, let's just go with intensity actually. Ambient light. Yeah, we're gonna give it a value, and then we're just gonna say color times ambient light, I think. Well, basically ambient diffuse plus ambient light times color, basically modulate by the color. And yeah, I think that should do the trick. And no, this shouldn't be vector, this should be float. And you see, we're just adding a bit of that thing. And you could also add, what is it called? Specular. Specular lighting too. Though I don't remember how would you do specular lights. I think you use power. But you need the camera then, and yeah, from now it becomes complicated even more. Yeah, I think this should give a little idea of what is going on with shaders to some degree. What do you think about this? Should I create some?
I think it's very fun and very interesting.
Should I create some tutorial about shaders next, or what? And
Sure.
math maybe. Anyway, so that's how I learned really a lot of math. I learned it just through shaders pretty much. So yeah, I was actually at some point in my math, in my education, I was like getting 1 degree in in math. One time I think I got 0, I'm not sure. But basically I sucked at school in math, kind of. Because it's just not super intuitive. Like they just like hold on. I mean, when I show you this description, when I show you spherical coordinates, like for example, parametric equation. When I see the definition of this, what do you understand from me? Parametric equation is a set of equations that express a set of quantities as explicit functions of a number of independent variables known as parameters. I mean, you can kind of, if you try enough, yeah, you could get it, but nothing defeats like actually seeing what happens and just playing with the equation, playing with the variables, and having some real world application, like problem to solve, basically. And that's actually how I learned myself. I'm not super good at like abstract mathematics and just trying to equations actually. So I just let the computer do the calculations, and I just play with equations, play with variables, and see what happens.
And you said that in real programs, usually spheres and circles are not calculated mathematically every frame, but shaders are on every frame. So I'm assuming if you were going to put a sphere in a program, that like the
I see what you're talking about. Now the thing is, I think I'm gonna show you using the Godot itself. Let's see, save and close for a second here. Let's make a 3D scene, for example. Let's see if I can figure out how to describe this. Let me first of all make some MSAA because my eyes are bleeding. 3D into aliasing MSAA, 3D slowest. There you go, nice, lovely. Okay, let's say we have some mesh here. Right, and let's say maybe this mesh is a sphere. Where's the sphere here? There you go. So this mesh actually contains vertices, right? So if we go to View tab here, and I show you, what is it called? Yeah, here. If I show the wireframe, notice that this sphere is composed of triangles. Now the thing is, to actually render this sphere, I'm not rendering to the whole window, I'm not like doing the calculations for the whole window. First of all, what I'm doing is I'm doing the calculations for this vertices. First of all, Godot is transforming these raw mesh data to, it adds it by projection and applies the projection matrix, the view matrix, the model matrix, and crazy stuff like that. I'm gonna explain that later on. Right now, I don't want to go that advanced yet. But yeah, that's essentially the case. And then after that, it goes through the rasterizer. And now what the rasterizer does, it figures out like which pixels are inside of these triangles, or actually which fragments technically. But just to simplify things, I'm going to say pixel, right? And basically let's say that fragment shader that I apply to this guy only runs on the pixels that are covered by these triangles, essentially. So not the whole screen like I had in my own script, So like, if we go back to this, where is it? Yeah, let's grab this guy. If we go back to this, here what's happening is that I'm doing all those calculations. I'm doing it for all the pixels, like for every single pixel, even these ones right here. I mean, I could try to discard those pixels, fragments and stuff, but anyway, just simplifying things. But basically everything, all the calculations happens there. But here the calculations are only happening in the triangles that are covered, like the pixels that are covered by these triangles. That's the first thing. The second thing is that instead of doing heavy calculations for every single pixel, what you do is you do some calculations on every single vertex instead. Like you have less vertices than you have pixels. So you do have heavy calculations as much as possible in the vertex shader, which runs only for every vertex. And then the GPU have its own kind of hardware stuff like hardware. Yeah, basically dedicated hardware to actually do the interpolation for you between those vertices, and it gives you like a good enough result while best optimized. But let me show you. Hold on. So if I display normal here, now notice that the lighting, I think right now it's actually being done on every fragment of the sphere. But let me see if I can change that. Hold on. New standard material, and let's see. Yeah, there you go. So as you can see, the shading mode here is done for every pixel that is covered by these triangles, by the geometry basically. And only, of course, only the pixels that are actually shown, like the ones that are like the triangles that are in the other direction are being culled. So that's another optimization right there. But here I could change the shading mode from pixel to either in shaded, which basically no lighting going on, no lighting calculations. But otherwise I could say, instead of in shaded, I could say per vertex. Now it's doing the calculations per vertex for the lighting. And you can see that there isn't much, like the per pixel is much more detailed, but you can't really see much difference. You see, because there's a lot of vertices kind of. But if I actually, let's see, if I decrease the, let's see, the vertices, let's say 32 here, or let's say 16, ring 16, for example. Now, this is what we're getting, okay? And now, let's try the per vertex. Yeah, we're already doing per vertex lighting. But I actually can, even then, I cannot really see a lot of difference. You see, per pixel. Yeah, that's very interesting. So it's pretty good approximation, doing the lighting per vertex instead of per pixel.
Is it the CPU that's doing the interpolation, or the GPU?
No, the GPU. The GPU have dedicated hardware to do the interpolation for the uniforms. Sorry, for the vertex data. I think.
Okay.
So let's actually try to show this even, emphasize this even more, maybe somehow.
Would this be more apparent on like highly detailed models?
Yeah, for example, this is a very low vertex, like low poly sphere, and look at that. Look at the lighting, how it is. Let's see now if I can notice the difference. Oh, it's already per pixel. Interesting. Interesting. I think maybe because we don't have too much lights. But yeah, hopefully you got the point. So like, as you can see, per vertex lighting is really enough for most cases. As you can see, you cannot really distinguish it between per vertex, per pixel. But yeah, pretty much disable ambient.
I'd say there's two ways to draw like circular objects, circles or spheres. The obvious way is to use a mesh that contains all the sphere vertices, but you can just use a fragment shader to make the circle or sphere.
Yeah. Now the problem,
but like if you use the fragment shader is like less efficient because like it is per pixel like all the time, or you like
yeah,
even
you would have to draw the entire screen worth of fragments. Yes, but you don't run any. You know that's 4 vertices, so it's a trade-off between vertex shader and fragment shader.
Yeah, basically that's basically it. It's like
I use both personally. I use the fragment shader for some of my radial stuff.
But what if you want a sphere bouncing around a room in 3D? Would you use a shader language for that, or actual mesh?
what do you mean? Like, you mean physics?
Yeah, like apply
like physics. Another thing, you know. Like, I could easily do this in Godot.
Would you write the circle using the shader language for
you have to keep in mind that like most games would just use a mesh for a sphere because it allows you to render the whole scene in one pass, right? Or like it allows you to render related meshes on the same pass, and that's usually what you want in a game.
So basically, in an ideal world, you're gonna have the physics engine and the actual rendering separate. You know, so like, I think Bevy have a good architecture for that. Let's see, Bevy rendering. Render architecture over there. You go. Okay.
Because remember, like if you're using a separate shader to draw the spheres, then that they're gonna draw on top of whatever was previous.
So like here is Bevy engine, for example. Okay. So here, what it's doing is actually having this extract path, right? Where it basically copies the simulation, like stuff from the simulation that it needs for the rendering. So like the positions of the spheres, etc., etc. But you can notice after the extract phase, both of them run in parallel. Like actual rendering and actual simulation are separate. You know, like they can even run in multiple threads if you know what you're doing. Like here, for example, the app world is, as you can see, being simulated separate from the render world. And then when in the extract phase, the data from the app world is being copied to the rendered thread, and then the rendered thread does its job while the simulation is still happening at the same time. So like you would have your engine, like your physics engine, like separate, doing its job separate from your, let's say, your rendering system. That's basically how it should work. So like basically your renderer only knows just what it needs to actually show to the user. Like for example, in a sphere that is bouncing around, as you said, like the renderer don't care. Just tell me what is the position where I'm gonna draw the sphere, you know. But who's actually doing the calculations if that sphere will bounce around and stuff like that? That's the physics engine that does the job. And actually that's where the model matrix and stuff like that takes into account that stuff. But I'm actually gonna go through that like when we actually implement that stuff in Vulkan, because soon we're gonna do that really, and you can see the whole experience basically. So yeah, hopefully that makes some sense. So yeah, I think we're done maybe with Goda. Is there any other question?
No, not right now.
All right, amazing. Let me see.
I'm gonna attempt to code some Vulkan on my computer. Last time I tried doing Vulkan in C++, I couldn't get it.
Yeah, no way, no way.
Work.
No way. You know, I wouldn't recommend C++ with Vulkan. Like, at least personally, I've gone crazy. I've gone insane. But really, Rust, I wouldn't really. I would go with Rust for sure.
Okay, and by the way, one more thing. On a previous stream, you said that SDL3 is almost, or SDL is almost at a point where it can program a game engine, but I think you said it was missing.
Yeah, it was missing shaders. It's missing shaders. Yeah. But basically, like, if I go to SDL right now, let's see, SDL GitHub GPU API, I think. So they're working on this new thing for SDL3. I don't know if I can find it. Let's see. Yeah, as you can see, they're working on, for SDL3, they're working on some GPU API, because currently in SDL, it doesn't allow you to do much. Like, it only allows you to do 2D, basically. You just, like, you know, give it a texture where you want to draw that texture, and you could also have, like, drawing some vertices, I think, like SDL draw vertices or something like that. It's actually pretty new. Where is that? Let me see the SDL documentation. Hold on a second. Libraries. By name.
go to the source code. Fuck all this shit.
Vertex.
Too hard to navigate.
What is it called? Geometry, I think. Yeah, there you go. So the only advanced thing they have currently in the SDL render, other than just 2D and, you know, like here is a texture, please draw it here, and here is a rectangle, please draw it, draw a sphere, like not a sphere, draw a circle, draw a triangle, whatever. Here you got this render geometry. This is the most advanced rendering function in SDL, and in fact it's the latest added one.
It's just a list of triangles. So
you just give it like SDL texture to use, the vertices, which I think are in 2D maybe, a number of vertices, indices, a number of indices. So yeah, they are in 2D, I think. Yep.
Java's graphics 2D beats this.
Yeah, because like SDL, they have to support a lot of platforms, right? So they were super conservative with what they do. Also, they have a software renderer. So yeah, that's pretty good for what they could have done. But right now they're actually making SDL3 and they're trying to make GPU API, pretty much. So
All right.
Yep.
Dio, is that how you say your name?
Yeah, exactly.
Would you say if I want to get a job at Rockstar, it's fine to learn Rust?
Good question.
I would say if
In
you
the
haven't
Rage
given
engine?
Rust a try, then it's probably worth giving a try. But I wouldn't say that that's any requirement at all, though.
But yeah, let's actually go back to
Might be a
Vulkan.
detriment.
I would say that if you're already comfortable with some language, then I would say stick to that and just keep going and work on something
You know what?
meaningful to completion. And as soon as you complete that, then maybe apply for a job.
Maybe C++ is my best language, but I've never successfully linked a library to C++.
Yeah, I feel you. Like, CMake was a very big pain for me. But like at some point I just, like I couldn't really download any library, so like I just gone through the pain anyways to actually learn CMake. It's like, that was crazy, but at some point right now I just have a setup that just works. Like if you see my latest CMake video, that was my setup of any CMake project, and it just works for almost every single insane library, pretty much. Now basically CMake is not a build system, but like CMake is just like build system of build system. Because C and C++ community is very fragmented. It's not like Rust where every single library have the same kind of documentation, the same naming convention, the same package manager, cargo, basically same
Crate.io.
Yeah, basically same everything.
Docs.rs.
Yeah, like the community, and even the community itself is very friendly and very helpful, while in the C++ community,
and very left-leaning.
Yeah, I don't know. So basically you need CMake to kind of just jumble all that, like handle all that garbage basically. But yes, that's why CMake kind of itself seems like garbage, because it's basically managing garbage.
Absolutely terrible.
It's crazy. So
that's why I don't use dependencies.
But in Rust though, the best when it comes to dependencies, the best when it comes to analyzer, Rust analyzer. Yeah, it's super good.
I gotta learn more.
The
about
only
Rust
thing with
analyzer.
Rust, the only thing with Rust is that you're gonna suffer at the start with the borrow check. Like literally, you're gonna suffer. It's like you're going to the gym. Bro, that's just crazy.
You know what's worse than that? I think lifetimes are worse.
Yeah, no way. Lifetime, yep. Even if you're advanced, no. Like you just, like if you see yourself or you find yourself making a lifetime in a struct, you gotta be careful. You probably want an arc, or you want to restructure your program or something.
Arc is the easy way.
Or an RC. That's basically, basically try to avoid lifetimes in a struct as much as possible.
Slow your program down by using reference count.
Because the thing is, when you're gonna add a reference to your actual struct, you gotta add it's kind of like error handling. You gotta actually make that lifetime and everything else. You're gonna bubble up that lifetime for your whole code base, and now suddenly your whole code base is just a hot mess of lifetimes. So yeah, but lifetimes, they're fine for if you're just passing them through functions, for example, or something. But basically, the Rust makes things that are pretty crazy and safe makes it pretty hard to do, basically. Anyways.
So right now, what are you actually making?
I mean, I'm just using the Vulkano thing. I'm not sure yet which project I'm gonna be doing. I'm thinking either UI or like in some sort of a little application, maybe voxel game. I don't know. We'll see how it goes. But currently, we're just going through the first stages, so I don't have to choose just yet. We're just going through Vulkano basically, and Vulkan in general.
Okay. And you recommend I should learn pure Vulkan before Vulkano, because you said that Vulkan's kind of harder in some ways.
Not harder, but it's pretty kind of abstracted, so you have to learn Vulkano abstraction itself, and a lot of times you want to see what like the actual like Vulkano itself, what it's doing in like behind your back, like in terms of raw Vulkan. You want to see what is going on. So like yeah, I would recommend going through raw Vulkan first. Just at least get your triangle, then go on with Vulkano, I think.
I personally would start with OpenGL because it keeps the distractions out of your way when you're beginning. 99% of the stuff, 99% of the code you're writing in Vulkan is irrelevant to a beginner.
It really depends, really. I don't know. But honestly,
it's not like Vulkan is anything different than OpenGL. They're just Vulkan is just more verbose toward a beginner. You still have the same pipeline. You still have the same exact,
Yeah, like the core concepts themselves are pretty much the same. But yeah. Anyways.
Vulkan does have that cross-platform additive stuff.
Yeah,
I will not write.
It's fragmented. You have like desktop OpenGL, and then you have OpenGL ES. I guess there's that fragmentation. But
oh yeah, the different types of OpenGL are kind of annoying.
Yeah. Anyways, so right now we're trying to make MSAA. We're trying to implement MSAA in Vulkano with dynamic rendering feature. So right here we're making an intermediary image. Okay, let me get the example as a reference here actually. And let's see. All right. So right now we have created this, which is basically given the image format, the image extent. Then the transient attachment here we can have in sample 4, basically multi-sampling 4x. So now we got the intermediate image. What's next? Here they're making final image, but we already have the final image, which is the actual Swapchain image. Right, so what's next? Now new default image.clone. No, I don't need that. And yeah, here they have a render pass. They're passing the intermediary with samples 4. Okay. So let's actually store this intermediary image now. Did I have it right here? There you go. Great. And let's see how I could do this. Okay, what is wrong? Because it's gotta be an image view, right? I see. Which is kind of weird to me. I think we do have to allocate some memory, but I don't know. Anyways, so we got an intermediate image now. What's next? Or maybe because it's intermediate we don't have to? I'm not sure. Anyway, we'll see. Okay. So now we got an intermediate image. Now let's go to the begin rendering phase. Vulkan render, right? Begin. Okay, so here. Now currently we only have one sample, so we're doing it Lloyd store and a clear value. Okay. Now here we gotta actually render to the, not to the Swapchain image directly, but we gotta render to the the intermediary image, which have more samples. So instead of this, we're gonna go, I think, with let's see, I think we're gonna go with self Vulkan, the intermediary image. I think we're gonna render to that first, and then do I need the reference here? Maybe not. Actually, I do. Okay, and what's next now? Cannot move. Let's go. All right, what's next? Clear value. Yeah, now I need to resolve this image into our Swapchain image. And how to do that? Let's see. Rendering attachment. Resolve info. And how do you make this in Vulkano? Maybe you pass in just the image view, possibly. And then here you say, and also one other thing why I recommend raw Vulkan first, because you probably wouldn't really appreciate how Vulkano helps you. So you gotta go with the pain first of raw Vulkan to actually understand why Vulkano is a pretty good idea. Anyways, self the intermediary image, self the Swapchain image. Swapchain image views, image index. How do you get the index again? Yeah, I think we already have it here. There you go. Okay, what's happening here? Option, I found range. What? I think we're missing a comment there, or what?
So you're most familiar with C++, Frisco?
Sorry?
Yeah, me.
Did you learn
Today
in
I was
school
just
or by
doing
yourself? Or?
by myself.
Nice.
Yeah. Today I was doing C++ in DirectX and Win32 API.
Nice. Is it fun using DirectX or not? I've never used it.
Well, at least at first it's easy. Our friend Kodotaku over here says that at a certain point it becomes hard and you get vague errors like
No, not direct. I'm not talking about DirectX 12 there. I'm talking about OpenGL
11. Oh, okay.
and WebGL and its family.
Okay.
For DirectX, I'm just not liking the API itself.
You don't like
the naming conventions.
the syntax and all that.
Yeah, I don't.
Okay.
I think Vulkan API is much more better designed and
Honestly,
more
Kodotaku,
consistent.
when you talk about the OpenGL errors being not descriptive, I feel like either A, it's pretty easy to find out what you did wrong because you usually just change something with regards to OpenGL calls.
Well, yeah, sure, for as a beginner, like as a small program, but
Yeah, but
Well, he was
eventually-
talking about like running on different computers and different drivers, right?
sorry.
You know what? Never mind.
maybe driver can be annoying, but yeah, that's true. But if it's a big project and you cause that OpenGL error, then you have a skill issue because you should have
Not
been
really.
calling correctly in the first place.
Not really. You know why?
Why?
For example, let's say I've explained this before, but basically, for example, this pretty simple example is your shader compiles just fine on your machine, right? On your driver, you know? And then suddenly you ship it and yeah, it doesn't work on other drivers. Why? Because your driver compiler implementation is more relaxed on the spec.
Yeah, but like
For
that's gonna
example.
be pretty
But
obscure.
there's a
call
lot of
if that's the
examples
case.
like that. And like, for example, stuttering. how are you gonna find, like sometimes you get frame stuttering because basically everything is done for you by the driver, and the driver have to guess a lot of things. So if you don't do the thing that it have guessed, there you go, it stops. But yeah, there's just a lot of stupid stuff. Anyways, here I gotta say Swapchain image extend, it's expecting I think 3D or something like that. 3, yeah. Okay.
And usually, like, if there is an error, everything else still works fine. So if you don't see something on screen that you meant to be seeing, then obviously it has to be related to that.
Why the image extend? Oh, I think like this maybe.
It's not like a seg fault where you don't know what the fuck happened where.
But I love my seg faults, my beautiful seg faults.
Slice indices are of type U size or ranges of U size. Super confused now. Where is image index? Oh, it's U32. It's U size. Bruh. Clone. You know, as long as it compiles, you're good.
Fuck it,
True.
copy this 2 megabyte piece of memory. As long as it compiles.
And let's see what's happening here. Oh yeah, the pipeline. I need to change the pipeline too. Let's see, Vulkan device. Yeah, I need to tell it the multi-sampling there too. Let's see. Multi-sample state, there you go. Okay, so for example here, I didn't get, I don't think I got an error from Vulkano, isn't it? Hold on. Where's the build? Not here. Here, yeah. So yeah, you can notice that I didn't get a error from Vulkano itself, but I got it because I have the Vulkan validation layer, the raw Vulkan validation layer, you know. And so if there is some error here, validation error, I know for sure. I can like read the problem and try to find out what's happening or why, you know. Or sometimes I even figure out like immediately, for example now. But yeah. Multi-sample state from multi-sample state? No, let's go with this. And let's say dot default as always, I think. And what is the defaults here? Sample 1, sample shading, none, sample mask. Right, alpha 2 coverage enable, alpha 2 1 enable. Okay, so I think need to change here the samples to what kind of
The stream. Is the stream picking up? Hiccuping for anyone?
Let me see.
Not for me.
Doesn't seem like it's fine.
Oh.
That's your drivers, buddy. You see what I mean?
Yeah. Sterilization samples, sample count. This should be 4. And yeah, now just remember that this is what we had before. It's very rough geometry. Right? Now let's see if this actually makes it better. Alright.
So this time you didn't use math for this. You just wrote some.
I'm not. I didn't reach the math yet.
You just told the GPU to use multi-sampling.
I think right now.
That easy.
It's not just that. I also made an intermediary image to sample to. Like, basically right now to add multi-sampling, what you do is you first of all create a transient intermediary image. transient meaning that we don't care about the result after the rendering is done. So the GPU can do some optimizations if it wants, especially on mobile hardware, where tiled GPUs, which most mobile hardware is like that, is using that. So yeah, I'm making this intermediary image, which of course should have the same format as the Swapchain, and the image extends same thing too. And then after creating that intermediary image, what I do, instead of here I'm using Vulkan like dynamic rendering, which only is available for Vulkan 1.3, or if you have enabled the extension dynamic rendering. But honestly, like dynamic rendering is much more intuitive and much more straightforward. And also when we have crazier architecture, we don't have to like track and create crazy render path permutations and crazy stuff like that. We just directly render stuff in, which is not perfect for mobile, but it's perfect for desktop. So here we're loading, we're clearing that intermediate. Now instead of actually rendering directly to the Swapchain image, what I'm doing here is I'm actually rendering to the intermediary image, which is actually multi-sampled. They have 4 samples in this case. And then after that, I'm resolving that multi-sampled image that I rendered to into the Swapchain image, which only have 1 sample. And that's how you basically do it. And multi-sampling, I think the best way to explain it is the Vulkan tutorial, MSAA, multi-sampling. There you go. There's some good thing right there. There you go. Okay. So here's what happens when you have 1 sample per pixel, I guess, or per fragment, should I say? But anyways,
it's disgusting.
Yep, it's disgusting. Like every pixel, it's very rough, right? So there's no smoothing. But then when you include like 4 samples, because basically why that's the case, because each pixel is binary, because they only have 1 sample. Like it's either the sample is covered or it's not covered. So you only have either 0 or 1 color, right? But when you have like multi-sampling, like in this case 4 samples, you have 4 states, like you have 4 samples basically. So in this case, for example, this one, it's covered by this and this and this, but it's not covered by this sample right here. So what happens is that you're going to get 3 divided by 4, which means like 0.75 coverage. So depending on that, you're going to change the transparency. And so you get this sampling like this. And of course, as much as you add the samples, the better the smoothing becomes, and of course the more you pay in terms of performance. And of course the actual and by the way, like the more samples you add, like you pay exponentially actually for performance. And also the fact that like the actual quality that you get kind of diminishes, like the benefit that you get diminishes per sample basically. But yeah, this is raw Vulkan, how you do it. Crazy stuff. But yeah. Anyways, so let's see if this actually worked really, because yeah, let's just make 1 window, please. Let's see.
I don't know about everyone else, but I've never actually really liked anti-aliasing.
I can never live without it. Yes.
I'm
Just
neutral
never.
on it.
Like I don't mind the jagged.
Like my eyes bleed, bro.
Yeah, the sharpness can cut your eyes if you look too hard.
Yeah, so let's see if this is actually working. I mean, I don't have any error right here, but let's see render doc. Let's run it. Now notice this is what we're getting currently without multi-sampling. Let's see. Let's launch it. No. And let's go. Now let's see. Notice, there you go. And I have captured the wrong frame. Hold on, let's get some colors in.
Oh yeah, you can see the transparency.
Yeah, there you go. And let's go. Notice that. So right now you can see that transparency. And this is just samples 4, and we could add samples however we want, basically, which is pretty cool. Now, I think we could see, interesting, hold on a second. Yeah, so look at that, nice. So you basically start with 2 attachments, well, not 2 attachments, but basically 2 frame buffers. You have, I think this is the intermediary image, and you have the Swapchain image. And then we come here, what happens is that you render to the intermediary image, which have 4 samples, you know, but you can see, of course, the intermediary image like is jacked. But it's kind of like it's more resolution kind of, but yeah, I have explained that anyways. And then it gets resolved to the Swapchain image. So you go from this, after the resolving in the Swapchain image, you go to this. See? Pretty cool. All right, lovely. So I'd like right now to make sure that this is kind of configurable. Let's see how we can do this. Vulkan device sample 4. How do we do this? Here. Let's say samples, sample count. And by the way, like this is dynamic rendering. It's pretty intuitive how we do multi-sampling. Though I still don't understand how render passes even works with that. This is how you do it with render pass. You have like these 2 stages, or these 2 attachments. Then you have the intermediary. Then you say like samples 4 here. Then do this weird stuff. Then you have this color, and then you say your color intermediary, color resolve, color what the. And then you have to manage frame buffers, and you have to manage the render pass. It's all weird stuff. It's pretty clear with begin rendering.
When I joined the stream, you were talking about Swapchain image.
Yeah.
What is that?
Like, let me try to find some other illustration here. Hold on. Let's see which tutorial had a better representation of that. I can remember there is a YouTube video, I think, that really explained this very well.
Like an off-screen image that's temporary that's about to be displayed.
So just the back buffer.
Yeah.
Okay.
The best video I found that really illustrates that is this one, actually. This was very useful to me back then.
See, in DirectX, we call it a back buffer. But yeah.
Oh, really?
Oh, yeah.
You still use Swapchain in DirectX, but you also have back buffer. That's what they're called.
Yeah, I've sent the link.
We'll see.
It's
the Swapchain that gets access to the back buffer.
Yeah.
But let me try to just get like, because I'm not sure this is like open sourced or not. Like, yeah, it's Creative Commons, so yeah, fine. Let's go.
The Swapchain. A Swapchain provides a collection of images which we can use in our render chain shell present the image and targets high. Taking a closer look, we can see that the update of the displayed image
this one is
must take less
pretty
than
good.
16.6 safe to interval between vertical blanks is not.
But I just want to
So
show
let's
the
return to the
Swapchain
immediate
part.
which serves as the data source for the image transfer to the monitor, swapping, therefore increasing the
There you
frames
go,
per
okay.
second. And let us assume that our application is really fast in drawing.
Okay, let's go from here.
We are in a similar situation as before, where one image is currently being presented within the Swapchain, and another image is handed over for presentation by the application. In this case, the image goes into the queue and waits until the next vertical blank occurs. Image 1 has been completely transferred to the monitor, then the vertical blank occurs. And the next image from the queue is put into the place of the presented image, and data is read right from its beginning, avoiding visual tearing. Let us add a few more images to our Swapchain, which we can do by requesting more images during Swapchain creation. This has the potential to increase the number of images that our application renders into in parallel, therefore increasing the frames per second. And let us assume that our application is really fast in drawing.
So the
So it
swap chain
requires
has
the
some
next image.
available images. I would expect image 1 to be discarded, though, but it's still
They're not really discarded, they're just being like cycled. Kind of like recycled, basically.
Rotated.
Yeah, rotated,
Renders
exactly.
into it and sends it for
But it
presentation
depends on the swap chain mode, you know. So this is just FIFO. But
to the swap chain, while image 2 is currently being presented within the swap chain. We acquire yet another image, render into it really quickly, and hand it over to the swap chain again for presentation. Now we have already 2 images queued, while presenting image 2 has still not been completed. Also meaning that no vertical blank has occurred yet. So our application
But
is
you can notice here is that it adds latency because, you know, you're rendering, but you're still like the presented, like you're kind of going to be presenting like an image from the past, you know.
running ahead in this case with respect to the swap chain.
So like how
But isn't
much,
it pretty fucking low latency? Like it's
like how
nowhere
much
near
images,
one.
like how much images you use with your swap chain and which present mode. It's basically a trade-off between latency, like how much frames you lag behind, and also frames. Like the more images you have, the more FPS you can actually theoretically get, and but also the more latency you have
Image is
in your
configured in
application.
C4.
Though I prefer Mailbox for, let's say, games or any real-time graphics. Why? Because it keeps on rendering. It keeps on rendering to the images, like just like immediate, just like what you would do without all this stuff. And then once the VSync is on, it just gives the freshest image that it rendered to the swap chain directly. So you have best of both worlds, but you're constantly rendering, so you're kind of basically wasting the images that didn't get presented.
Full presentation mode.
I
The
tried
application, of course, does not stop there.
4
and
images
2 has
and I
completed.
saw no FPS increase over 3.
It depends really
On
on
my
your
machine.
application, pretty much. Like if you're just throwing a triangle, a lot of these things doesn't really matter. But yeah, you could actually watch the video later on. It's pretty goes into details. I think it's the best video I've found on the topic, honestly. Yeah. So right now, what we should do, we added MSAA. What else? Should we add 3D now? What do you think? What should we add now?
add a health system.
Health system?
Oh, by the way, you were using rendered docs, right?
Yeah, render doc.
What is that?
It's basically for debugging. You see like every command that happens. You see the images that are currently being, what is going on with the images, what are their formats, what are the resolution, what are their, like what is the colors exactly are. You could see the image however you want. You could see the range, blah blah, whatever.
It's quite a nice tool.
Yeah. You
I
can
do share the
also,
complaint with you that it doesn't save the last application that you just launched. That's
there's
kind of
also
annoying.
the like primitive topology, then the mesh view here. You could see the mesh that you're rendering. Here is the input of the mesh. Then this is the transformed mesh after the vertex shader, you know. So this is the actual raw data, and then this is what the shader transformed it to, and this is the actual swap chain image, right, or viewport basically. You can see the raw data, and then you can see the transformed data after the vertex shader. You can see the
So do
you can see all the resources that you have, like the fences that you have, graphics pipelines, blah blah. You can see some statistics, like how much buffers you have or you're using, etc. And yeah, there's a lot of cool stuff here. Yeah.
So do you run the Rust code from Rust Rover and then it'll catch it? Like present information, or
No, you actually initiate from here. Or you do attach to running instance, but I don't know how to make this work, honestly. I think maybe I have to add some logic to my code to actually make it work. But yeah. But this is how you basically do it. You just launch, and there you go. But of course the FPS is kind of low because I have validation layers on, and also I have VSync on. So
and validation layer is just for debugging, right?
yeah, just validates your stuff. Anyways, all right. So I guess let's try.
I'm gonna go learn some. I'm gonna go learn some Ash right now.
Yeah, I've done that tutorial on Ash too.
Which tutorial?
Let me see. It's actually a lot of people like that tutorial for some reason.
What's Ash?
Ash is the raw Vulkan binding in Rust.
Oh, I see.
Let me see where I can find my tutorial here. Where is it? Yeah, this one. Video. Yeah, I've gone through a lot of stuff. Like this is raw Vulkan basically. Can see a lot of unsafe. Like unsafe is everywhere. There's literally no frame in this video that doesn't contain unsafe code. It's pretty crazy.
Where's the how do I know that it's unsafe?
It tells you. It
because
doesn't
it says
compile.
unsafe.
It doesn't tell.
It literally says unsafe. Okay, yeah. Yeah.
Anyways.
All right.
So right now,
yeah, I'm gonna go learn that.
Yeah. Okay. I'd like to actually group my buffers using the sub allocator. Let's see. For best perf, I think. And then I'm gonna try, I guess, to load some objects from like mesh data from actual OBJ files. So let's see how we could do this.
Are you gonna use a library just to load OBJ file?
Sure. The best libraries are in Rust. Because this is not an OBJ tutorial. Anyways, let's see. Where do I need that stuff? Vulkan device, right? And first of all, I want to, instead of using two buffers for my vertex and index buffers, I want to use one buffer and just sub-allocate in it. So here's how I'm gonna do this. Well, actually, let's load the textures really. Yeah. I guess let's add textures first. But yeah, let's actually group these buffers first. Currently, I have multiple buffers. So instead of that, I'm gonna go with the sub buffer allocator, kind of like this. But this one, instead of staging buffers, it would be for the device local buffers. So prefer device. And I want, yeah, that's it pretty much. Just prefer device, I think. Yeah. And here it should be transfer src, actually transfer dsc in our case. And it would also contain the other buffer usages. Now, according to the maintainer of Vulkano, he told me that it's fine. Just combine the usages of the vertex buffer and the index buffer. Like, it doesn't really have any effects currently with the drivers, except I think for NVIDIA for uniform buffers. But anyways, index buffer and transfer DST. And now what's next? And also this arena size, by the way. Instead of vertex buffer size, I should probably go with instead with vertices.len with .size actually. Invites, so like std size of val mem size of val vertices plus std mem size of val indices. So I'm basically packing the indices and vertices in the same staging buffer here. And just doing this is crazy in Vulkan because you gotta make sure you do the alignment correctly, a lot of other stuff. Vulkano is pretty easy peasy because it handles the alignment for you and all that stupid stuff. So now that's the arena size. Okay, nice. And that's the first one. Now the other one is this guy, which is like the local device subbuffer allocator, basically. I'm gonna call that one device. Okay, great. Now let's go with this. Basically gonna be the exact same thing, really. I have a lot of copy paste currently. Anyways, right, as device size. And what's next now? Vertex index buffer, great, preferred device. So this would be in VRAM. So not the allocator itself, but the buffers that it's gonna allocate. So basically I have multiple subbuffers, one for the ones that's gonna be in the VRAM and one for the staging buffers, which can be in the host. Basically, so device subbuffer allocator. Great. Now how we do this? Now instead of creating a new buffer every time, we just gotta say device subbuffer allocator dot allocate. And also in raw Vulkan you would have like, you would deal with raw bytes, but here in Vulkano these subbuffers are kind of like views. They basically contain also the type, so they can make sure to handle alignments very well and make sure it's type safe. So allocate size, allocate slice, great. Now here I'm gonna give it just the length, which is vertices.length, I think. So instead of giving it how much bytes, I just give it how much vertices actually, as device size. This is a result. Okay. Now let's create an index buffer too. Indices.len. Great. Now what? Why it's not using an index buffer? Interesting. Let's see. Oh, what? Oh, it's shadowing. Okay, so we don't need this anymore. It's basically boils down right now to just these two allocations, pretty much. Vertex buffer and index buffer, and then this other allocator. Honestly, let me group these. Let me put it here, and let's just call this something more meaningful. Let's call this host buffer allocator. And let's call this honestly, let's just call it device host allocator. Oops. Bro, I need to learn some Vim. Device allocator. Come on. Bruh. F2. Okay. There you go. Great, 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 great. And in fact, this is basically the same, like maximum data kind of. Great. And now what? So we got device buffer allocator and host buffer allocator, and here we're allocating staging buffers and we're allocating vertex local buffer basically, and then we're writing to them. Nice. This should be the exact same thing, but instead of using two buffers, we're using one. And use the import buffer, blah blah blah, whatever. Oh, samples here. I gotta add the missing fields. And here it would be just samples. And for that we're gonna go with, now instead of hard coding this, where is it? Samples, there you go. And rasterization samples. I'm not sure if I want this on the device itself, but for now let's just put it here. Okay. There should probably be some other stage between the Vulkan device and the Vulkan render, like some sort of Vulkan context between them, where like the pipeline and the buffers could be shared between multiple windows and stuff like that. But anyways, whatever. So let's go with Vulkan device. Where we're creating it. I guess we're creating it here, yeah. Here I can choose the count. Let's go with sample 8, why not? And let's go. Now just gonna make sure in the Vulkan render that I use the samples instead of hard coding it. I'm gonna go with the, well, device, I think dot sample. Well, Vulkan device, right? Samples. Oh yeah, I see. So can I generate that? Let's see. Should do the trick. All right. Though I'm gonna just make sure that it actually puts them in one buffer. Just making sure I'm not doing this wrong. I think I found a way to do that. Let's see. Like for example, we could try to maybe say let's say this, and vertex staging buffer possibly. Well, I don't know why it doesn't give me autocomplete. Let's see, dot buffer. I'm not sure if I can do this, but let's see. So the underline buffer, are they the same or not? And same thing with the other guys. So just making sure that they're indeed in the same buffer. Cheek to cheek. True, false. Ooh, interesting. So the second buffers, for some reason, this ones aren't really the same. Well, that's interesting. True, false. Okay. Let's see what we have done wrong here. Index buffer, vertex buffer, index buffer, vertex buffer. Actually, how does that even work? Yeah, I see. What if I try to kind of align this to, let's say, 64 or something? How do you align values in Rust? Well, for now, let's just give it some offset. I don't know, let's say 64 bytes or something. And let's just make sure this is actually the problem. Yeah. True, let's go, yeah. It's an alignment problem, I see. So I think just to be safe, the maximum alignment is gonna be 64, so we could go with that, I believe. But I'm not sure how to align stuff, though. Hold on. Rust align value. Not really align, but like the closest to some value. Round, kind of. Round to value. I know how to do this using round, but is there like a dedicated function? Doesn't seem like right. Weird. But yeah, okay, fine, let's go with that. Dot round. What's happening here? Yeah, well, it's not giving me any. Oh, because it's not interesting. Not really. That's not really what I want. So what I have here, I have usize, right? Okay. Rust usize docs. See if you can find something there. Let's look for round maybe. What? Like literally there's no. That's not what I want. How I was doing it myself manually. I think I was like making it into an F32 maybe. as f64. Then we gotta say round, and then here I'm gonna say divided by right alignment, which is 64 in my case, and times 64. And just to make sure that I'm doing this correctly, that's a lot of parentheses right there. But let me just make a little function actually. You're gonna get like a number that is usize, and actually maybe even like it could be generic possible, but anyway, never mind. Number usize, and let's go with an alignment. Fine, let's go with usize, I guess. And return, well, basically first of all we're gonna cast the number as f64. Oh, I don't need return. And this should give us a usize. Number has 64 dot round. Oh, what is this? Rounds returns the nearest integer to an f32. Weird. Oh, what I'm doing as f64 dot round, and yeah, here we're gonna say divided by alignment times the alignment again. Finally, cast all of this into usize. I think that's how it should work. Number as alignment dot round times alignment as usize. I think so. Maybe. If I'm not missing anything here. Can we go to Rust Playground real quick? And let's just print, I don't know, let's say line usize, let's say 54,64 for example. Let's see what this would give us. Cannot multiply f64 by usize in here. Actually, hold on. Can't we just say times alignment after that? I guess. Yeah, should be possible. Shouldn't change anything, I guess. We got 64, nice. If I say 32, I get 64. Amazing. If I say 11, 0. No, I don't want that. I want it to basically seal, not round. Yeah, I want it to seal. So it will make sure it never goes to 0. There you go, nice. So if it's 11, then it's go to 64 and so on. So now if I say 64, of course it would stay the same. But if I say something like 65, There you go. It goes to the next alignment. Amazing. Yeah, I think that's what I need here. And I'm just gonna be conservative and go with 64 as the alignment, because it's basically the maximum. Maximum initial data size. And yeah, here I'm just gonna take this guy, Rich, and gonna say align view size, the number is this guy, and then the alignment, let's say 64. And this should do the trick. So we'd make sure we have the same buffers no matter the alignment. Although we're wasting some bytes, but who cares? Oh, what the? What? Why it's still false? What about 128? And I'm gonna remove my headset for a second. If someone wants to talk, let me know. Okay. Well, for some reason it's still not doing the trick. What? Maybe I'm doing something wrong here. This is .len as device size. Oh, it's true, weird. What is the size of the vertex? 3, but we have alignment, so it's gonna be maybe 16 plus 16. It's gonna be like 32 bytes, I think. Something like that. I don't know. Not sure. So we have a problem with who? With the vertex buffer and the index buffer themselves. We don't have a problem with the staging buffers. Why? It's probably because of alignment, but let's see. Allocate slice vertices.len and indices.len. Oh, by the way, I don't see the chat anymore. Interesting. Okay. Alright, so I'm missing something here. Well, I guess what we could do is, I think, creating the vertex buffer, index buffer first, and then what? Yeah, I don't know. Let's just leave it like this for now. But basically right now, we're actually using one buffer. Well, two buffers. One for the staging, which just get destroyed because it's just a temporary, and the other for the actual device. So right now I'm just gonna have a break and then we can come back. So Okay, we're back. So let's try to actually load some OBJs, I think, at this point. Let's look for some library for that. Cargo. Well, crates.io. Almost 3 years ago. What? 8 months ago. Okay, let me see. Rust OBJ. April 29. Okay, great. Alright, normals, texture coordinates, and vertex color. Amazing. Flat data. Indices, materials, features. Very nice, cool. So you basically say you load the OBJ, you give it the file, and if you don't mind missing the materials, you can generate a default. Number of models, models.len, materials.len. Then we go through all the models, right? Then we get the faces and let face in 0 to mesh.face aritize. What is that? Aritize. What? Face aritize. I don't know why they have to make it complicated every time. Okay, hold on a second. I guess maybe we're gonna make our own parser. I don't know why it's always very complicated. Anyways, if I create a cube here, I'm gonna remove everything except for the cube. Don't want anything else. And yeah, let's try to render this as an OBJ and let's see. Also, what about glTF? Let's see glTF how it is. Just normal glTF. Export with separate JSON binary and texture data, easiest to edit later. And there's glTF. Less efficient than binary. Okay. And let's just see what this would actually give. And I'm gonna include, let's see. Renderable objects only. Think, or yeah, it's fine. Who cares? My up data material. I don't want any material for now. For now, just go with vertex. Like just the positions of the vertices. Maybe you could go with vertex color is fine. But anyways, never mind. We'll just go with the simplest. Shape keys, nope. Armature, I don't know. Skinning, probably not. Lighting, unitless. Fine. Animation, nope. Anyways, let's try to export glTF and see how it looks. I don't think we can actually handle glTF. Gonna need its own live stream now. But let's see. Oh, what is this? Is it really? So it's actually JSON, which is very interesting. Asset generator version, scenes, name, scene nodes 0. And in the nodes, we got mesh 0. And then the name cube. Then in meshes, we got name cube, primitives, attributes, there's only position, nice. And there's indices 1. Great. Accessors. So this is just JSON, bro, nice. Yeah, the binary, that was actually hard to manage, I think. But anyways, accessors, there's buffer view 0. And the component type, the count. Where's the actual data? Oh, it's in a bin file, isn't it? Yeah, it's in a bin file. Interesting. Open with Kate if you can. But like, how to handle that bin folder? I don't get it. Not sure. I have to actually read the spec for that, but yeah. Let's see. What if I exported using, let's see, desktop, fine, and let's go, instead of separate, let's go, I guess, with embedded. And let's see how it looks. Let's see. So right now it's in one file. It's in base 64. Oh, okay. I see, in base 64. Well, that's interesting. And I guess it would contain all the stuff. And here you got byte length and the byte offset. And so you got 2 buffer views, and the 2 buffer views only go with 1 buffer, so buffer 0. And for the position, it's buffer 0, like buffer view 0, I think. And yeah, and then the indices is buffer view 1, I guess. So like byte length 72, well, that's 96. Byte offset 96. Maybe we could actually manage to do this actually. That's very interesting. I mean, we're not gonna parse the whole thing just yet. Is there any library? Let's see. Yeah, I mean, I want, at the end of the day, I want glTF, no OBJ, but not sure how hard it would be. Let's see, reading glTF documents plus its buffers images from a file system, from the file system. Great. I don't know, I guess let's try glTF anyways. Is this still maintained? Last week, yeah, it seems like, which is interesting. Yeah. Okay, let's just go for it, fine. Okay. But before that, honestly, I'm gonna add this stuff into the, just like basically MSAA. Oops, let's commit all the changes so I could revert if I couldn't figure out how to work with glTF, because this is gonna be a ride. Let's see. Okay. Wish me luck, I guess. Cargo add glTF. Though I'm really gonna need to actually probably read the spec of glTF. Anyways, cargo add glTF. There you go. Hopefully Vulkano would help this time, because last time I tried it with WGPU, it was a horrible mistake. But it was C++, so I don't know. Maybe Rust would be sane. Yeah, let's go. Let's try this out. So, what this actually gets, by the way, hold on. Sorry, not this. Let's see. So glTF, it takes a glTF. Can it take glb? I don't know about that. Not sure, but let's just start simple with whatever they're doing here. Just one file that contains everything, which is this guy right here. Great. So let's take this guy and call it, I guess, box or whatever. Cube, right? Cube. Let's call this cube. Let's grab this into our beautiful project. And let's come here, assets, directory. Is the stream fine? Yeah. Assets, and let's basically add the asset there. There you go. Now we got the glTF there. Nice. Now let's actually just copy paste as much as we can. Read the implicit buffers and images from the file system. Walk in the node hierarchy. Do I want to go with this or do I want to go with that? Let's go with this for now. First, and let's see what we got there. Basically, does our thing run? Let's see. So currently I'm probably going to remove the color attribute for now, just to keep things very, very simple. Come on. Though later on I'd like to use glTF to like get the camera, get the scenes, get everything basically, even the lighting, PBR, blah blah blah. But right now we gotta go step by step. So yeah. All right, let's see. Let's see. Vulkan render. So how are we gonna do this? I think they should probably go in app RS actually. But I think for now, just to keep it simple, I'm just gonna do it in the Vulkan device for now. But anyways, it's probably gonna have its own asset system basically instead of the visual system. Well, whatever. So here, basically, we're gonna go with this. And actually, by the way, first of all, before this, let's make these vectors and make sure that everything is good with that. And also, let's remove color attribute for a second. It should be pretty easy to remove. Okay, good, lovely. Great. Now let's actually remove the color. Yeah, I actually want to remove a lot of stuff right there. In fact, yeah, I see. Well, you know what? Let's just keep everything there for now. Fine. And let's go. Okay. So let's actually do this. And glTF import. And for now, we're just gonna do it this way. /assets /cube.glTF. Actually, let's go with assets /cube.glTF. I think. Can I change the working directory? Yeah, it's actually correct. Okay, great. So assets /cube.glTF. Nice. Actually, I'd like to create another folder called, let's say, models or meshes or well, I don't know what to call it. Anyway, never mind. So now let's see what we have here. Assert EQ that buffer's length is equal to document the buffers.count. Okay, lovely. And let me put a breakpoint here so I can see what's happening there. And let's go. I'm probably making a mistake by starting with glTF. Let's see. Okay, so document buffers. There you go. This is the document. So it contains index 0 and it contains accessors but let's start with something simpler, which is like buffers, for example. So you only have one buffer, which of size 1/68, I think bytes. Yeah, bytes. And you have all the bytes in. Amazing, lovely. What else? We have the images. Of course, we don't have any images in glTF scene just yet. And the document. Yeah, so what is in? So yeah, the only thing that right now we need to figure out is the document, I think. So the document contains 2 accessors. And what else? Animations, nothing. It contains 1 buffer, 2 buffer views, and meshes. So let me just open up the stuff that is actually have something in there. Currently I'm gonna hard code a lot of stuff. I'm just gonna try to just get the data, extract the data directly, hard code it as much as possible. So we got the accessors, and what is else? There's buffers, byte length 1/68 with the name, nothing, URI. Okay, extensions, extras. Okay, so buffers, 0 byte length. I think it contains only the byte length, but why it contains all this data here? Weird. Like, okay. Then the buffer views, which also contains byte length and which buffer it's talking about. And then it contains the byte offset 0. Okay, byte stride. Nothing. So byte offset 0, name, target, extensions, extras. And then we also got another buffer view called, well, not called, anyway, so buffer is also getting the data from the buffer 0. And essentially we got a byte offset of 96. Here we got an offset of 0, of course. And a byte stride, it doesn't really tell the byte stride. Interesting. The name, the target, element array. Oh, okay, this is the actual yeah, the indices, right? Element array buffer. The target here is vertex buffer, right? Array buffer, right? So the vertex data. Great. But like, why it's not giving me the stride then? It's telling me none. Interestingly. So okay. And in the scene we have, of course, one scene, though it seems to be empty for some reason. Okay, don't care. Extras, meshes. Okay, we also have meshes, and we got like extensions, no extensions, extras, the name of the mesh, the cube. Great. And then a vector for some reason. Why there is a vector here? 67, 117, 98, 101. What? Primitives, only have one primitive, and oh, I think here where it contains the attributes, right? So length, alloc, extensions, extras, indices. So we got the indices, which is an accessor, and it's have one here. What does that even mean? I guess maybe it starts from index 1 or something. Material, of course, nothing. I disabled that. Mode, triangles, of course. Targets, nothing. Weights, nothing, of course. Nodes. And the nodes 0 children extension matrix nothing, except for the mesh, which we have 0. Okay, we got the name here for something cube nodes. Okay, so I think nodes basically defines the hierarchy possibly, and like the rotation, the position, the scale, like the matrices. Okay, I see. For the scenes, what's happening here? There's a name. Yeah, it's called just scene. Okay, makes sense. Then extras, extensions, nothing. Okay, so we're only interested into this field called buffers, so we can get the data, I think. Yeah, we can get all the data from here that we need. And what else gonna need? Gonna need this attributes probably to get the attribute kind of layout, I think, but we could just try to hard code it, I think, for now. So yeah, here what we got, buffers. Okay, extension scene byte stride. Yeah, interesting. The first one, 96 offset. Is it U32 or what? Let's see. So like the element array buffer. Yeah, like the byte length is 72. How much vertices in a cube? Well, those includes the triangles, like, but anyways. I would guess U32. So let's just try to hard code this and see if we can do something here by any chance. Let's see. So we got the buffer, right? So let's say so buffer is equal to buffers dot into iter whatever dot next. I'm just gonna move it out of the vector. I don't care about the vector anymore. Just hard coding stuff. And now what is this? Windows first align to SPDR. By the way, is there any helper functions in here? Accessors for reading vertex attributes from buffer views. Okay. Interesting. Cameras and their projection, read buffers and buffer views, accessor, import buffers, import images, blah blah blah. Accessor. So we could say accessor offset from buffer views. Yeah, I'm just gonna assume some things and let's hope it works. Pretty much. Let's see. So I could go with 0, right? And then I got my actual buffer, which is just a vector, seems like. Okay, a vector of U8s. Lovely. So that buffer contains both the indices and the vertices, which actually is really what I want, but I still interesting. But like I don't know. I think we should go through the document and at least get the offset to kind of like split the buffer, basically. So document dot views probably, yeah. And here we're probably gonna have like 2 views or something like that. Get buffer data, huh? No, let's just keep it simple. Views. I think there was 2 views probably. So let's take the first view, which was the actual vertex view. Which is an option. Okay, just unwrap it. I know for a fact that it exists. And the index buffer view. Index buffer view. Now let's see. Vertex buffer view dot. So here we get the actual buffer. Nice. We get the index, get the offset, extras, length. Okay, that's very interesting. Not gonna lie. Righty. Buffer, index, and offset. But can't you just give me like a slice? Invites between vertex attributes or interleavable data. Interesting stuff. Okay, so I think maybe I don't even need the buffer really here. I could just infer it from here. So now let's try to do this. So vertex buffer view dot buffer dot, what this would give me, into like, what is this? Hold on, it's a buffer, but yeah, now how do I access the data of the buffer? What? I guess he only gives me the index then. Yeah, I think so. So yeah, we do need the buffer. That just contains an index to the buffer really. So okay, great. Now if we want the vertex data here, it's basically buffer, and we're gonna go use a slice here. And in fact, it's gonna be vertex data. Well, anyway, let's just go ahead and say vertex buffer view dot offset. The vertex buffer view. I think the length of the buffer view in bytes. So yeah, that's correct. And hopefully that would contain the vertex data. And then the index data would probably contain this. It would contain the index buffer view. Great. Can I just debug right now and see what's up with this now? And I'm probably gonna try to cast it. Use OK or to provide an error compatible with where this is the case. This was in 147, I guess here. This function returns a result. What do you mean? Well, if it returns a result, then yeah. I guess it's not compatible, right? With that result. So anyway, I'll just unwrap this stuff. And here we, of course, yeah, we want to slice it like that. And since that's the case, okay, let's go with, look at that. The Rust compiler telling me exactly what I'm missing. Let's go. It would have been better if it just fixed it. So anyway, okay, so this should separate the vertex data from the input data right now. Sorry, for index data. And interestingly, the same size. What? How? I guess maybe a coincidence. I don't know. 96. Okay. So our vertex. Well, yeah. Let's remove color, please. Let's remove color. Let's keep things very, very simple. Color, remove it from here. And what we're doing now, We're gonna remove this color from here, and we're gonna keep the frag color there, and instead of passing in some color or whatever, we could just say, we could just pass in the position as the color. Well, it's vec3 frag color. Okay, yeah, great, lovely. And the other thing here, we got position. Okay, let's just remove that stuff so it doesn't get in the way. So we're just gonna keep it as position. For now, I'm just gonna leave the push constants. I don't want to mind with that right now. Later on, yeah. But anyways, so yeah, this should do the trick, I think. Now, I'm gonna try, I believe, to reinterpret this or something like that. But so basically, this is 96 bytes, right? This probably is, well, I think it's 16 bytes because of the alignment, possibly. Maybe. Or maybe not, no. Maybe not, yeah. No, that was for the push constants, I think. For the vertex, I think it's fine. So this would be like 32, which means 4 bytes, 4 times 3, which is like 12. So 12 bytes. And 96 divided by 12. 96 divided by 12. 8 vertices, huh? That's correct, right? 8 vertices. And that's nice. So we're going in the right direction, I think. 8 vertices, right? So how much indices then? It's gonna be, so it's also 96 bytes divided by, but like the vertices, the indices are probably 32. So they're gonna be 24, I think. Yeah, that's probably correct. So can we reinterpret this? Maybe reinterpret or something, I don't know. So I guess maybe we don't need this anymore. But like this is gonna be the vertices and this is gonna be the indices. But we're gonna use bytemuck, I think, to cast this, right? So we have bytemuck, and let's cast a slice, I believe. Bytemuck like this, and let's go. Bytemuck for the rescue. It's even infinite for me. That is amazing. That's what I would expect from Rust, but it should be U32 though. Okay, so where I'm actually hard coding U16 here. So let's go with U32 for now. And what else? Here too, same thing, U32. I probably have to still change some other things then. U16 here too. U32, right? Great. Do I have some U64 here or something? No. Okay, so U32. I may need to change some other places, but this seems to be the ones that I need to change currently. So is that correct by any chance? Vertices, indices, bytemuck, cast slice, we're casting them. Yeah, if anything goes into plan, this should do the trick. And we're getting nothing. Interesting. Maybe it's because of calling or something like that? Possibly. So let's make sure that is not the case by too simply, let's see, back do call mode none, so I can make sure that is not the real problem there. Okay, right now we're seeing something. Oh, why does it broke? Which is this? That's weird. Why this happens? What? Ooh, so something super weird happening with our swap chain for some reason. Interesting. But like, why? No idea. Something funky happening there with the swoop chain. The swoop. Let's see. Max image count, current transform. Window size into. I don't really see why. Okay. Okay, I see. We gotta recreate the intermediary image because the swap chain gets recreated. So, yeah, I see. All right. So self dot intermediary image. We gotta set it to something new here, and I believe maybe it's gonna be very similar here. So just gonna probably say. Intermediary image. Let's just do it pretty quick. Let's not overthink this. Let's just copy this for now. Yeah, let's just copy this for now, and let's go. Here we gotta go with self the Vulkan device. And yeah, self dot. Let's not really overthink this now. We don't have the time for that. I'm not sure why it's not formatting my stuff. Okay, there you go. Self, and there you go. Okay, this should probably fix it. But I gotta make sure maybe to destroy it first or something. Anyways, let's see. This should probably work out just fine. Yeah, there you go. Pretty cool. So, yeah, this is what we're getting. Well, this is where render lock would actually help us. Let's see. Launch application, launch. Okay, let's capture a frame and let's see what's really happening right there. Because I can't really tell because we don't have a camera yet, so we could go to let's see, to the mesh viewer, I think. There you go. And yeah, as you can see, the vertex input is correct. Lovely. As you can see, we're actually loading a cube, which is amazing. Can't believe I used glTF. Although, of course, I'm hard coding a lot of stuff. But yeah, it works. So now what's up with the vertex output? It's weird. What is happening here? This doesn't make any sense, does it? Yeah, why it gets... Can I see orthographic maybe? No. What is this? But yeah, we're getting the vertex, the vertices that we want. Oh, actually, well, yeah and no. Why the triangles doesn't show up? Let's see. Weird. Vertex output. Okay, let me try to figure out what I'm doing wrong here. Let's go to the shader. And let's see, where's the shader? There you go. go up there, and here we're sending the position in there, and we're setting the fragment color to the position true. I mean, this should be good to go. Time. What could be the problem here? Like, it's only drawing one triangle for some reason. What? Oh. Are we doing the right vertices count, by the way? Well, good question, I don't know. Let's see. Bind vertex buffers. First binding. Oh yeah, vertex buffer dot length. I knew it. Okay, let's use the index buffer. I didn't notice this because the indices length was the same as the vertices length up till now, and we have some panic here, interestingly. Oh, are we even using the index buffer actually? Hold on. I think I'm doing it super wrong here. Hold on. Yeah, indeed. I need to use draw elements here. I don't even know how this actually works so far. It just ignored basically the index buffer, which is very interesting. Anyways, draw indexed. Control Alt Shift O. Let's see if GitHub Copilot would understand this. Yeah, great. First index 0, vertex offset 0, first instance 0. No, just go with one. And the index count, great. Index buffer length, great, lovely. Now let's see. I can't believe we had all this, this whole problem, all this time, because we were just drawing one triangle, so I didn't really notice. Okay, and right now I'm not seeing anything at all. Interesting. Okay, let's see this guy again. Let's capture and let's see what's up with this. Mesh viewer. Let's go here. What? This time it doesn't do anything? Weird. Draw index 24. Or maybe the index buffer is wrong. Oh yeah, look at that. It's kind of like initialized. Well, that's interesting. What? That's very interesting. Index buffer dot length, index count, instance count. I'm binding the index buffer, which is correct. Binding the vertex buffer too. So maybe yeah, possibly it's using E16 instead of U32. Possibly. Let's see, Vulkan device, U32. So let's try to replace this by U16 and see if that's the real problem there, by any chance. Or maybe I'm missing out on something here. So yeah, let's try to replace this, not this, replace this, and replace this, and yeah, that's it. Let's see if U16 is the right thing here. I mean, this we should actually infer from the glTF, but we're just trying to make things work now. Okay, and yeah, it doesn't work. Interesting. Let's launch the application again. Yeah, I don't think it's U16, it's probably U32, but something weird is happening here. Let's see. Pipeline state, mesh view, and so the VS input. PTX, IDX. Yeah, that doesn't seem good. Position, draw indexed. Where's my bind index though? Yeah, it's trying to draw 48 indices. What? Isn't 48 too much? I don't know. Command buffer, pipeline layout. So we're binding an index buffer. Type UN16. But yeah. Weird. Very, very weird. I don't know. Like before we had it just fine with U32 actually, just that we have added draw indexed and somehow now it doesn't work. Maybe the indices were not loading them correctly somehow. So that could probably be the issue, because before I have actually noticed that the mesh was getting loaded. Right, the actual vertices themselves. Oh well, oh well. Draw indexed. So we're saying here indices.len index buffer. Hold on, glTF to index type something. GL2 specification. Yeah, let's see if we can find something about index buffers here that could be problematic or something. Vec3 float. Normal tangents, we don't have any of that now. Okay, hold on a second. Let's just go back to U32, and I'm gonna try something here. U32, finally U32. Okay, so go back to where we need to go back, and let's see. So if we said, yeah, let's just actually do this, or let's just do this really, and let's see what's going on with that data and try to figure out if it's correct by any chance. In fact, we could even, yeah, I have a good idea. Let's export as obj, and let's don't include UV coordinates, don't include normals, don't apply modifiers, whatever. Don't export any material, and let's export wavefront obj, and let's go with that. Home. Anyways, let's see. Obj, let's go. So I guess these are the vertices, the faces, and stuff like that. Okay, nice. So let me put this here, and let's go. So, and let's make sure we're doing this correctly. Okay, so here we got vertices. We got 8 vertices. Yeah, there's indeed 8 vertices. So 1 minus 1, correct. 1 minus 1, correct. Yeah, I think the vertices are probably all correct. Minus 1, 1. Yep, indeed. So yeah, the indices are probably the issue here. So like we have how much indices? We got like 6 faces, I think. Yes, 6 faces. And we got, for each phase we got 4 indices, so 6 times 4, which is 24 indices, and it's indeed 24. Alright, but for some whatever reason this is what we're getting. Okay, I see. So we have a problem here. Okay, interesting. For some reason it contains garbage data, basically. Okay, my bad. I always forget about this. Damn. Yeah, honestly, I'm never gonna write it like that anymore. I'm just gonna do some little trick here, which is to always go with this. I think that would probably make sure that wouldn't happen ever again for me, because I always forget about that. What about the indices now? Oh my god, what? It's still incorrect? What in the world is this? Okay, let's try the solution I had before, maybe. Index buffer dot offset. And this plus the length. Let's figure this out. Let's see now. Hopefully this time it would work. Come on. The size is correct. It's just that the data somehow is weird. Damn. I mean, why that could be even the case? Buffer index buffer view offset to buffer view offset plus index buffer view dot length. Could it be that the offset is like from the actual offset of the vertices? I mean, yeah, that could be the case. So Yeah. I don't think, no. I mean, it returns the offset into the parent buffer in bytes, so... That's super weird. Is this in bytes? This is also in bytes. Yes. So what is going on here? This is super weird. Okay, let me see. I have no idea what to do at this point. Super stupid stuff. Let's see. Alright. Index buffer view. What is happening here? We got the bytes, right? The byte offset 0. What? Why the index buffer is 0? What? That doesn't even make any sense, does it? Weird. Like, what? Okay, hold on a second. If we go to buffers, buffer size. Where's the document? There you go. Let's see. Buffer views 1. So byte length 72 and the byte offset is 96. Let me just hard code it just to make sure. 72, 96. 96, 72. 96, 72. 96. 72. Okay, let's try this out. Indices. This is super ridiculous. Could it really be 16? No. Well, it's size 18. Ooh. Why that's the case? 96, 96, 72. That is honestly very weird. Very weird. Go back to what we had. Index buffer view, document.views.next.inwrap. Weird. Really wanted this to work, but for some reason vertices, indices, index buffer view, index 0, JSON parent, byte length 96. Doesn't give that thing, so let's see. Why it's saying 0? This is stupid. Byte length. What? Byte. Bruh, I'm super confused right now. Oh well, anyways, let's leave this for later on. Anyway, so yeah, that was it for this live stream. So see you in the next one. Goodbye.